Okay, so good afternoon to all of you. So we are starting the fourth session, which is on heterogeneous architectures, which is, I think, quite high topic those days for our models for weather and for climate. And so we have prepared, we have asked for a set of talks. So we start with Claudia Frauen. So maybe introduce yourself as well. So I'm Sylvie Jousseaume, I'm the coordinator of ENES-RI.
And I'm Italo Picoco, you already know me.
And then we start with Claudia Frauen from DKRZ on preparing icon for heterogeneous architectures, experiences, and the way forward. So the floor is yours. Claudia, we will tell you 5 minutes before the end of the 20 minutes. So then after that, we have 5 minutes, okay? 5 and 5, okay?
Perfect. Okay, thank you very much for the introduction. And yeah, I was asked to give a bit of an overview about where we stand with ICON in terms of, preparing it for heterogeneous architectures. And I will split my presentation in two parts. So in the first part, I will give a bit of an overview where we are today. And then in the second part, I will give more an outlook and introduce some new initiatives and a new project, Warm World, which was already mentioned before, which will hopefully start soon, and what we are planning there in order to go forward. And so for those of you who don't know ICON, I think most of you will already know it, just a quick overview. So ICON stands for icosahedral non-hydrostatic model, and it is a weather and climate model with atmosphere, ocean, and land components. And it has been developed now for almost 2 decades, initially by the German Weather Service, DWD, and the Max Planck Institute for Meteorology, and later also the Karlsruhe Institute for Technology and the German Climate Computing Center, DKRZ, joined as official partners. And now there's also a close collaboration with the C2SM in Switzerland. And the model is mostly written in Fortran and uses MPI and OpenMP for parallelization. And it has around 2 million lines of code. And if we now look to the future, what we want to do, we're really interested in running ICON at kilometer scales. And there has already been a lot of effort in that direction, so especially in the HDCP Square project, which enabled the efficient kilometer and hectometer scale applications over large regional domains. And this work then also enabled the use of ICON to perform the first global storm resolving simulations in Europe. And ICON is also one of only 4 models worldwide to have been run as a storm-resolving Earth system model. That means with a coupled model with kilometer scale both in the atmosphere and in the ocean. And why are we interested in these kilometer scale resolutions? I think here's a nice graphic from one of my colleagues, where on the left-hand side you can see a snapshot from a simulation with the MPI ESM at a resolution of 80 kilometers, which was kind of typical, for example, for CMIP5. And on the right-hand side, from a recent simulation with ICON at R2B10 resolution, which is approximately 2.5 kilometers horizontal resolution. And you can really see the differences, and especially at this kilometer scale resolution, how also these small scale cloud features can really be simulated. And this resolution is also really important because it allows us to directly simulate the vertical energy transport in the tropics, which is the most important mode of energy transport there. Of course, when we do these high-resolution simulations, it's also very interesting for us to look to the large GPU-based computer systems like Pitstained in Switzerland or now the Jules Booster. And the GPU port of the atmospheric component of ICON, ICON-A, was motivated by the QBIC project, which stands for Quasi-Biennial Oscillation in a Changing Climate. And recently also a paper was submitted on the work that was done for this GPU port by Giorgetta et al. And a preprint is already available via the EGU sphere, so it has been submitted to GMD. And there are also a lot of details in this paper that I can't go into now. But some of the key decisions was firstly to stay mostly with the original ICON Fortran code base and add OpenACC directives to really allow portability so that it can run both on standard CPU systems and on GPU systems. Then there was a need to replace the radiation scheme because PSRAD, which was used before, would have needed a significant refactoring or rewrite, and it was unclear how much could be gained by this for running on GPUs. And so the decision was made to switch to RTE-RTMGP, which works efficiently on GPUs and also on CPUs. And for the land component of the model, JS-Bach, the Claude tool, which is a source-to-source translator, was used for the GPU port. And here I can show you just a figure from the Giorgetta paper, which shows the single-node GPU-CPU speedup factor. And I know it is always not really clear how meaningful those numbers really are, but I think especially if you look at the single components and see that really overall components of the atmospheric models, we achieve really a speedup. So what you can see here is a comparison between the Intel Xeon CPU nodes on pit-stained and the NVIDIA Tesla P100 GPU node. And you can see that for almost all the components, the speedup is between factor 6 or 7. Only the land physics is a bit less, but I think this is likely due to the small computational kernels there, though the kernel launch is quite expensive. But on the other hand, also the land physics are only a small part of the computation, so it doesn't really impact the overall performance. And then for the radiation, which is really one of the expensive parts of the computation, there was also a lot of effort done towards optimizing it. And so there we see an even larger speedup. And if we're now interested in the overall performance, we have seen before already that simulated days per day is always an interesting metric to look at. And so what you can see here is on the x-axis, the number of nodes, and on the y-axis, the number of simulated days per day that were achieved on 3 different systems. So the red cross indicates the pit-stained system, where the initial GPU port was done for. So that was the first attempt on a GPU system, where on 1,024 nodes, we achieved a throughput of around 50 simulated days per day. Then came the move to the Joules booster system, and that didn't mean not only the newer hardware, so we have the A100 nodes, but there was also significant effort to further optimize the code. And so there we can see we can run on 128 nodes with a performance of around 130 simulated days per day, or on 256 nodes with over 200 simulated days per day. And what I should also say here, this is a very specific configuration for this cubic experiment with 191 vertical levels, which is quite a high number. So for a standard climate simulation, I think about half the number of levels is sufficient. And so we could then assume that at a 5 kilometer horizontal resolution with 91 vertical levels, I think it is, on Joules booster, we could already get around 1 simulated year per day. And for comparison, what I put in here with the black crosses is also our new Levante system at DKRZ, which is a system with AMD EPIC CPUs. And what you can see here, so this was really a first shot, so it's not really a fair comparison because the system is really just going into production now and there was no optimization or anything done. But you can see that on the CPU system, especially, we see the very good scaling up to 1,024 nodes. And even though, the overall performance is not yet where we would like it to see, so I think there's still some room for improvement. But still, also CPU systems can really be used also for this kind of high-resolution simulations. So to summarize on this part, the atmospheric component of ICANN has successfully been ported to NVIDIA GPUs using OpenACC directives. But there are still some issues. So the Claude tool that was used for JS-Bach is no longer supported or being further developed. So an alternative is needed for this. And the ocean component of ICANN has not yet been ported to GPUs. And there's work ongoing to do that. And at the same time, there's also work ongoing to run the coupled model hybridly on the Joules system in Jülich, which means that the atmosphere would run on the GPU partition and the ocean on the CPU partition. And I think if you have some questions about that, Luis is also here, who can tell a bit more about that. And then, of course, the interesting question is also, what about Lumi? But also, as Luis already said yesterday, we are quite hopeful that with the Quake compiler, we will be able to compile and run the current OpenACC version of the ICANN A code also on the GPUs at Lumi. Or as an alternative, what we also tried on some small kernels during a hackathon last year would be also to create kind of a source-to-source translation tool to transfer the code to OpenMP. Okay, but now looking forward, we have quite a lot of projects and initiatives that have just started or are about to start, which aim on further developing ICANN. And so there's the Warm World project that was already mentioned before, which is a German national project initiative, which has been proposed to the BMBF and will hopefully start in September this year, although it might be a bit later, with a lot of different institutions and universities in Germany involved. And at the same time, there's also the ICANN-C initiative, which is a coordinated effort involving all the ICANN partners, so C2SM, DKRZ, DWD, and the MPIM, which really aims to rewrite ICANN for scalable development on emerging architectures. And we also have the Pre-Warm World project, which I'm a part of, which is a preparatory project for Warm World, which has been separately funded by the BMBF and already started last year. The project partners are the DKRZ, the JSC, and the MPIM. And so what are the goals of Warm World? The aim is really to assess the detailed trajectory of global warming and the quantitative implications of this warming for human and natural systems. And in order to do that, we really need a coupled ICANN model running with an acceptable simulation quality on kilometer scale, with a throughput of more than half a simulated year per day by 2026. And with kilometer scale, I really mean 2.5 kilometer horizontal resolution or less. And we want to develop ICANN-C, which stands for ICANN Consolidated, which is a free and open source software implementation of the fully coupled ICANN model to enable scalable development. And at the same time, we also want to develop integrated workflows to expose the information of ICANN alongside IFS-based solutions and observational data. And Warm World consists of 4 different modules. So there's the Better model, a module which is responsible for defining and testing the model configurations. Then the Faster module, which is really responsible for transforming the ICANN code base into an open, scalable, modularized, and flexible code. And this is also which I will talk about in more detail later. And then we also have the Easier module, which is responsible for developing novel methods to make information visible, accessible, and interoperable. And the Smarter module, which aims to involve also the applied math and informatics communities to improve the workflow and the model performance. And of course, Warm World doesn't stand alone, but it's really embedded in a larger environment. So there's very close collaboration with the ECMWF, which is also actually a partner in Warm World. And then there are also a lot of overlap and collaborations with projects like the EU project NextGEMS, with ACROS and Maelstrom. And especially for the Faster module, and now also already in the Pre-Warm World project, there's a very close collaboration with the C2SM in Switzerland. And the objectives of the Faster module are to really transform the ICANN code base into an open, scalable, modularized, and flexible code, which will then be named ICANN-C for ICANN Consolidated. And for this, we really want to refactor ICANN with the goal of scalable development to enable portable performance improvements and ultimately to make ICANN faster. And then also to initiate target performance ports to meet the throughput goals that I mentioned earlier. And we also want to progressively redefine the ICANN code structure to expose areas of performance improvement, also for the targeted exploration of new programming concepts. Okay, thank you. And yeah, so we really need a major ICANN redesign. And for that, Warm World is just one piece of the puzzle towards ICANN-C. It actually is a much larger coordinated effort involving all the ICANN partners. But this also means that there really is a need for balancing between different needs. So on the one hand side, ICANN is run as an operational numeric weather forecast model. And on the other hand, the scientists want to do cutting-edge climate modeling and climate science. And then there's also the Exclaim project by the ETH Zurich, which I should mention here, which stands for Extreme Scale Computing and Data Platform for Cloud Resolving Weather and Climate Modeling. And their approach is to rewrite ICANN code into a descriptive user code based on Python, which is then translated into a standard imperative language, like, for example, C++ for specific architectures using a toolchain based on GT4Py, which stands for Grid Tools for Python. But there are some, what I would call ICANN realities that we have to face. And ICANN is really a largely monolithic code. It has a huge code base that is compiled in. Name lists are used to activate or deactivate large tracts of code, and there's very minimal unit testing. And even though Git submodules are used, only very few can be decoupled from compilation. Also, the components are not very cleanly separated. And a big issue is also the use of very complex Fortran-derived data types. And we assume that there's also lots of unused code, but it's a bit difficult to detect it because, of course, different use cases require different parts of the code. But within ICANN, we have started with some first development steps. So we're really working on refining the development process. As a first step, there's a need to implement kind of a disable functionality, which will initially just be done via ifdefs, but it will really help also with a cleanup. Then we really need to work on the modularization of components, and there's already a proposal and prototypes are being developed. We also need a prototype for new data and memory management. There are other infrastructure measures that we are tackling, and we really also need to work on the testing hierarchy and the tools. And so I said pre-Warm World was funded by the BMBF as a separate project to prepare for Warm World and to facilitate also timely coordination with external projects such as Exclaim. And the aim of pre-Warm World is really to provide kind of a technical blueprint in terms of modularization and programming paradigms. And there will be an overlap between the latter phase of pre-Warm World and the start of Warm World to allow these plans then to be coordinated before delivering the development environment in terms of repository, test structure, licenses, and so on for use in Warm World. And one of the main goals of pre-Warm World is also an assessment of programming paradigms. And for this, we want to take a granule or not a kernel, it's larger than a kernel, but a part of the model that is cleanly separated and use it to evaluate, compare, and then develop prototype implementations of the selected module using modern programming paradigms targeting heterogeneous hardware. And so we really want to take this granule and implement prototypes, first using the Grid Tools framework, then using a generic DSL approach like NEDSL, which is being developed by some universities in Germany, implement a prototype using a domain-independent generic library like Cocos and/or DPC++ or SYCL, and finally also implement a granule using the concept of an embedded DSL, which is being developed in Jülich. And we also want to analyze the applicability and, if suitable, implement the interfacing of the above concepts to the front end that has been developed in the ESCAPE2 project. And so, to summarize, the atmospheric component of ICANN has been successfully ported to NVIDIA GPUs, although hopefully it will also work for AMD GPUs using OpenACC directives. However, to go forward now, we really need a significant rewriting and refactoring of ICANN for scalable development on emerging architectures. And this is really where this ICANN-C initiative is aiming for. And we have this pre-Warm World project, which is working on an assessment of programming paradigms and modular software blueprint. And steps are already underway in pre-Warm World together with partners in ICANN-C and Exclaim to, on the one hand side, rewrite the memory management in C++ with a C-Fortran interface, which would then also allow to attach components which have been rewritten in other programming languages than Fortran. And we're also preparing a standalone version of the atmospheric tracer advection as a playground on which we then can try out different programming paradigms. And if you're interested in more details of really the technical details of the ICANN-A GPU port, I can really recommend you this paper by Marco Giorgetto and others, which has been submitted to GMD, and a preprint is available online. And that's it, and thank you for your attention, and I'm happy to take some questions.
Thank you very much. I let Italo for the questions.
Yes, we got some questions in the Google Doc. So the first one is Kim. Kim, please, could you?
Thank you for the talk. In one of the slides, I read that you want to transform icon code into an open code name icon-C. How sure are you, we understand open? Like you are licensing through any open source strategy, or that you want to make more accessible, or?
So it is still under discussion because, of course, all icon partners have to agree. But as far as I understand it, the plan is really to have it under an open source license.
One question from the room.
No, it's extending the answer. The problem is that there is a special law for the German Weather Service, and that means that the code is critical infrastructure for Germany, and it cannot be made open source as it is today. So they're currently working on changing the law, and you can imagine that that's not done in a couple of days. Usually that takes a couple of years, and it's ongoing since a longer time. So it's not that we don't want to, it's just that it's not possible for the time being. We try to be as open as possible with these two kind of licenses, one from MPI and one from DWD, but MPI cannot make it really open source due to that. Sorry.
Okay, we have another question from the Google Doc from Nikolai.
Yeah, I think you get it a lot, but is the GPU-enabled icon and the sort of usual icon as two different code bases? And if they do, how do they communicate, like updates if some PhD student worked on?
No, it is really one code base. So that is what they said in the beginning. So the decision was really to stay with the Fortran-based code base and add this OpenACC directives to have the one code base that can run both on CPU and on GPU. And for example, also what I showed was the performance numbers. That was really exactly the same code that has been run on the Joules booster that I also managed to run on the Levante system.
Great. Just also another small question. What, and maybe also for our audience in the room, like what happens with dwarfs? All of a sudden, like dwarfs disappear, and now we have granules. Is this the same thing, or it's we just inventing names?
I really don't know what the best definition is. We choose granules because we really want something a bit larger than just a dwarf. So a granule, for example, is really the whole atmospheric tracer advection and not just a small part of it, because we want really something that's representative for the full model, but still that we can separate from the model to use it as a playground to test out.
But the dwarfs are, as a concept, are dead now, or what happens to them?
The concept of dwarfs has been invented by somebody else.
Okay, so Sylvie, do you have a couple of questions?
My questions are related to the human resources behind all this work. So whether you have an estimate of the first step, which was the porting to the with OpenACC on of the icon atmosphere, and the second one is the rewrite. Do you have estimates and how much time, resources? And I mean, that's my main question.
For the first part, I would refer to Louis.
So for OpenACC, I would claim that at the end, with the evaluation of a lot of strange things, it's about 15 man-years.
15 or 15?
15. And but that involves quite a lot of evaluation of, for example, Claw, the predecessors of GT4Pi, so grid tools, and waiting time for vendors to fix their compilers, which you can easily eat up to 5 years in total, where of the 15 man-years, the people have been idling because they couldn't proceed. So you see, it's a quite different story. So I think you could have done it in 3 years with one person if all the tools would have been decided in advance and all compilers would have been working properly and all machines would have been working properly from the start. So that's a lot of ifs. And you can see it's not easily that you throw on manpower, but you need to have a real developer-friendly environment. And there's a big big thanks to CSCS, which has been providing a lot of investment into this, in terms of extra people working on things which are not really related to GPUs in the first place, but supporting everything around it. And that's usually not counted in this many years you put in.
And for the rewrites for the future?
I think it's even more. So, I mean, we are in the lucky position that both with the Warm World project, which will hopefully start in the fall in Germany, and the Exclaim project in Switzerland, there are really a lot of resources available, but also, yeah, a lot. I think the biggest problem is that when you hire new people, they don't have the in-depth experience with the model, so there's also a lot of effort needed from the experienced ICANN developers, and so, yeah.
Thank you very much, Claudia.
We have just one quick question from Sam. What HPC facilities will be used for a Warm World project? Which facilities? Jewels or?
Yes, so definitely Jewels. Also our Levante system at DKRZ, and I'm not sure if Lumi is also, I think Lumi is also planned, or, I'm not sure, but I think also then with Destination Earth and other projects, so we're also definitely targeting Lumi.
Just to comment on this, I think every machine in Europe which has a larger GPU capacity will be at the end target, either because the computing center are asking for applications which are GPU ready, and they come to you, do you have a problem to run on it? That can easily happen. And insofar, I think it's every major platform having GPUs will in one or the other way be involved or used.
Okay.
Okay, thank you again, Claudia.
Yes.
We can move to the next one.
Then we have Eva Kavcic from the UK Met Office. She is online on the PSyclone experience with her in the Met Office, evolution and revolution. So the floor is yours. Yes, hello.
Hello. Hi, good afternoon all. First question, can you all see my presentation on the full screen, and can you hear me?
Yes, yes.
Yeah.
That's fine.
Okay, cool. Right, then I'm just going to go to crack on. Okay, so what I'm going to talk about today is how we use PSyclone into numerical models that the Met Office is either actively developing or using, or both. Evolution and revolution refers to the idea of using this tool to optimize the existing code, and also using this tool to basically to work with the optimization with the code that is written with the tool in mind. So how we also write the this atmospheric model to better utilize PSyclone, and what can we achieve with that. And it is a work of many people, some of which are referred here, and hence I will give a very high level overview. I'm happy to answer some questions, and I'm happy to also point you to the people who will be able to give you more details. So I'm going to quickly talk about, just revisit what is the motivation to basically create and use PSyclone. And I'm going to start with revolution, and that's the use of the PSyclone in the ELFRIC atmospheric model in the ELFRIC API to better contrast the evolutionary part after that, and that is the use of PSyclone on the existing code in the NEMO Ocean model. I won't go into details about what the NEMO Ocean model is. I believe that Italo has already given a talk about NEMO and its performance this morning, so you are very welcome to refer to his talk for more details. So, to just briefly revisit the motivation for this entire story. So the entire story of PSyclone began with the scalability problem for the current Office unified model with the endgame dynamical core, and that is on the Lathlon structured grid. When you want to increase global resolution, then the resolution around the polar caps, the spatial one, becomes really fine. So one of the challenges of the increased resolution is the exascale computation, and that means that we need to parallelize the codes for the future architectures, and we don't quite know what are the architectures going to be. The scientific code can be very, very complex, as we heard from the presentation just now, and rewriting it and adapting it can take a lot of time. So the idea was to basically, since the single source optimized code is unlikely to be possible, to try to actually keep the single source science code and to somehow use an automated tool to try to achieve these 3 Ps, the performance, portability, and productivity, and to create maintainable high performance software. The idea that also came from this entire Gung-Ho project was the idea of the separation of concerns between the science and code optimizations, where the algorithm layer would do the mathematical operation on the entire field, structures like the time stepping, spatial discretization, and so on. Then we would have the kernel layer, which would be also written by scientists, and they would be basically operations on data points of these unpacked structures. And then we come to the parallel systems, or the Psi layer, which is the pure computational science, where the optimizations are applied, and that would be the generated code. And this code generation is leading us to PSyclone, which is literally cloning or generating of this parallel systems layer. So it is a domain-specific compiler for embedded DSLs. As I mentioned, it's currently supporting the ELFRIC atmospheric model, the NEMA, and Ocean. So it's currently translating Fortran to Fortran and OpenCL. It supports distributed and shared memory parallelism, and it supports code generation, which is the revolution part that I'm mentioning, and code transformation of the existing code, which is the evolution part. So this is a tool that basically records the knowledge of the HPC experts. It is a tool for the use by the HPC experts, and they can use different and explore different transformations. So we talked about, there was an interesting discussion just now about hiring people to port the code to new platforms and how much time it could take for a complex scientific code. And the idea that basically PSyclone has that this knowledge of optimizations are encoded as a recipe to apply, rather than baked into the scientific source code. So it enables scriptable and whole code optimization. PSyclone uses the tool called Parser, which is a pure Python Fortran parser that supports Fortran 2003 and some of 2008. It can fully parse the unified model, ELFRIC, and NEMA source. There is some work in progress to parse the IFS, and it's used by the PSyclone stylist, which is the application used in the Met Office to check the code style and Loki. Right, let's get to the revolution part. and that would be the ELFRIC API, and that is where the aforementioned code generation comes into play. So the ELFRIC API processes code written in a DSL embedded in Fortran. It follows the PSyclone code structure that I presented before, and it works with this generated Psi parallel systems layer. So to just briefly introduce, the ELFRIC is the new modeling system that the Met Office is developing for the preparation for exascale computing. It utilizes the Gung-Ho dynamical core. So I'm just going to outline the differences between the current and the ELFRIC. So the current works with a mixed, with the finite differences method on a horizontally fully structured lat-long grid. And the Gung-Ho dynamical core in ELFRIC has mixed finite element method with the horizontally unstructured, vertically structured quasi-uniform mesh. In the the optimizations are hard-coded. In ELFRIC, we are generating them using PSyclone. So one of the things that comes with the horizontal unstructuredness is that the horizontal adjacency is lost, and that you basically have to store a lot of information on how to access the data on the mesh. We still have the vertically adjacent cells which are contiguous in memory, so ELFRIC basically operates on columns of the data. This entire class of new information that we need to store and access is leading us to the ELFRIC infrastructure. So unlike in the we don't have just Fortran arrays anymore to store the prognostics and diagnostic fields. We have data classes. An example of them is a field, and then for the mathematical operators, we have classes like operator and scalars, and the entire plethora of the supporting classes where we store the information from the global mesh and MPI partition and so on. That, of course, brings the challenge, and that is the compiler support for the object-oriented Fortran 2003, which is very mixed, and we are constantly working on improvements to the code. Another thing which is quite important is because we have the horizontally unstructured mesh, and we are looping over columns of cells, we need to basically be careful how we update these columns of cells when we are looping over them in the horizontal. It is very important whether these cells are sharing the data points between them, which are these so-called continuous function spaces, or are not, which are these discontinuous. So ELFRIC infrastructure stores the tools for that as well. It's basically stores the information about the mesh, about the fields, and because it works with the classes, it's not only the data points and values, it stores the methods how to update these data structures, and it supports looping over cell columns, as I mentioned, and looping over the degrees of freedom or data points. And what is very, very important to mention here is that PSyclone cannot work in ELFRIC without ELFRIC infrastructure. What PSyclone basically does here, it generates call to the ELFRIC infrastructure to unpack the data and to provide the correct looping limits and other information. So how does PSyclone know what to request from the ELFRIC infrastructure? This is where this DSL embedded in Fortran comes into play. And I mentioned kernels before, which are basically doing the operations directly on the data points that is on the column of data, which can be seen from the keyword operates on equal cell column, and what I mentioned before about the discontinuous and continuous function spaces is encoded in the kernel metadata, for instance, any discontinuous space, W3, W2, and so on. And as you can see from the slide, we have different metadata for how PSyclone accesses those data. Are the data just read, or are they updated? So this was the kernel layer. How do we know that in the algorithm layer that PSyclone needs to be invoked? This is again, we have the DSL embedded in Fortran, and we have this word called invoke. Basically, this is a pseudo Fortran call where we call directly the kernel types. And as you can see from the algorithm layer, there are no details about data structure whatsoever. What basically algorithm operates on are the field objects, which are the instances of these classes that I described. So there is an example of a kernel, which is the handwritten science code which I showed before, and a built-in, which are the operations on the entire fields of the data points, which is something that PSyclone provides. So this is how the DSL embedded in Fortran in the algorithm and kernel layer signals PSyclone what to request from the infrastructure. I won't go into the technical details of the generated Psy layer code. I am happy to show some additional slides on request later if there are questions. So just to summarize how this ELFIC DSL Psy layer works. So the algorithm and kernel,
Eva, 5 minutes. Sorry, it's difficult to talk.
Yes.
Eva, 5 minutes.
Right.
Thank you.
Okay. Then, so we are basically taking the information from the algorithm and kernel, create this language independent in Psy intermediate representation, and generate parallel Fortran code. I'm just going to quickly then give an overview of how we work with NeMo. NeMo is quite different because we don't because it works on the existing code that follows strict coding conventions, and because of strict coding conventions, it recognizes certain code structures and constructs higher level internal representation, and this is what the transformations are applied. So if you look at the NeMo DSL, the Fortran parser is used to parse the existing code. It creates the intermediate representation. The NeMo API is providing transformations, and it generates the parallel Fortran code. And here is the example of the NeMo transformation. So this is the original NeMo source code. And unlike in ELFIC, the source code itself in NeMo is, from the PSyclone point of view, treated as a manually written Psy layers with all kernels inlined. And this is what the NeMo coding conventions are enabling. So there is no algorithms algorithm layer as in the ELFIC API. So how does it work? We are using then fparser and PSyclone intermediate representation to generate the PSyclone schedule of this nested loop over the levels, the latitude, and the longitude showed in the NeMo source code before. Then, on this slide, you see how this schedule how the layer intermediate representation looks like when the OpenMP parallel directive is applied to it. Basically, the entire triple nested loop is enclosed in it. And this is what the generated code looks like. As you can see, the loop over levels Latin long is still there, and PSyclone basically inserted the OpenMP parallel direction. So all loops, so this is an example where all loops are parallelized over vertical levels using OpenMP. The NEMO API also supports the open ACK transformation, and this is an example of the evolution of the NEMO Orca 12 performance on GPU plus MPI using PSyclone. And I think that since there is a lack of time, and I think that Italo has already showed this, again, please do refer to his talk. I am also happy to give some more details if required. So how do we proceed from here? So I hope that I have shown that we can achieve the flexible optimization using the PSyclone principle of separation of concerns. And I have some slides which are basically demonstrating that using the flexible optimization plus the knowledge from the API, we can show the performance improvement. What is also important to note is that there is a lot of sharing of knowledge between different PSyclone APIs in the Met Office. For instance, the results that I showed before were for the NEMO performance on GPU. So now we are working on running the ELFRIC atmospheric model on GPUs. And we used the NEMO API, the open ACK from the NEMO API, as a starting point for this work on ELFRIC, and it's now progressing well apart from the usual problems with the compilers. Also, an example where PSyclone in ELFRIC can help PSyclone in NEMO is how we incorporate PSyclone into the ELFRIC build system, which hopefully can help into how NEMO is built with PSyclone as a part of the process in the Met Office. And that was what I wanted to show. And thank you very much for your attention. I will be happy to answer some questions.
Typically here as a PSyclone. So how do you see? So you mentioned it will be maintained by the Met Office. Is that what is meant, or because it has been developed by STFC? So how do you see? And when the other part of the question, sorry. So go. Sorry.
I think something was wrong with my internet connection. So if you could please repeat the question. Thank you.
What about the long-term maintenance of PSyclone? How do you see that? Because that you report the problem to this to the PSyclone, all the porting, the adaptation.
I am basically the embedded PSyclone developer in the Met Office. So the main developers are Rupert Forden and the Porter from the STFC. And my job in the ELFRIC team is basically to work with everything Cyclone in ELFIC, from the development to the management of Cyclone releases for ELFIC and so on. So this is a long-term plan. It is, I am the main developer, but there are other people in ELFIC in other teams who have also contributed to Cyclone. So we are building this knowledge base, and we are also liaising with the NEMO developers in the Met office to work on how we use Cyclone for all, because it will likely be that we may not all use the same Cyclone release at the same time, and yeah, so there it requires a bit of coordination. The question about how we report the issues, basically, we who are working with Cyclone in the Met office are in regular weekly contact with the STFC. We do part of the work, or they do part of their work, and we test the improvements in the Met office as part of the development process.
Okay, thank you again, Eva. We can move.
So we have now Gijs van der Oord from the Netherlands eScience Center on accelerating tracer transport in FISM 2 with GPUs.
My new version? I don't know if it's my new version to start with. Let's see. Maybe I'll get that surprise. Thank you for inviting me. My name is Gijs van der Oord. I'm from an institute. Microphone. I'm from the Netherlands eScience Center. We are involved in EasyWays 2. We are not a Met office, we are not a supercomputing center, but we are a research software engineering institute, and we help national academics, but also participate in international projects like EasyWays. So the work that I will present has not been done by me alone. We have had big contributions from Atos, David Guibert and Herman Raffin have worked on this as well, and then my colleagues from the eScience Center, Alessio Sclocco, Ben van Werkhoven. And then from Alfred Wegener Institute, I will mention Natalia Rakovsky, Nikolai Goldunov, and Dmitry Sidorenko. Let me go forward. So I want to use this gathering to also highlight a bit our easy ways to service on model refactoring and porting, which I had a lot of fun working on. It's still going on, by the way. This is, I think, a very important effort in easy ways to service the European community of Earth system modeling at large. So it's an outward-looking effort helping them initiate or contribute to their porting efforts to GPUs, but also more general optimization efforts and studies. So this is a service that is still going on, and I hope we will continue it if the follow-up project is agreed. And a quick overview what we did. So we had a call sent out to as many Earth system modelers that I know, and we offer 6-person months of expertise from our research software engineers from Netherlands eScience Center and Ethos to these groups spread out over Europe. So, for instance, in Cyprus, we helped people on the IMAC Medina chemistry, atmospheric chemistry with speed up of their CUDA ports. In Delft, we did some mixed precision for DALES, a large eddy simulation for the atmosphere. And also in Wageningen, radiation code porting. I'm currently involved in the regional climate model at Trieste. They are interested in using OpenACC for acceleration. Blom, well, this is not University of Bergen, this is Norse that I should mention here. We're also involved in Agrif in Grenoble. Grenoble is not there, but I know that. And of course, so FASOM 2, which was actually awarded twice 6 p.m. So 1 person here has been has gone into this effort. So FASOM 2, the finite volume sea ice model, is well, we have experts in the room on this model. It's being developed open source, and that's actually, I think, something still a kind of special. It's not only just put open source on GitHub, it's actually being developed. So you can see the pull requests, you can see the discussions, the issues, and it's all out in the open. And you can use it if you want, etc. FASOM is making, I mean, its entrance in the European landscape. I would say it's coupled to EGAM 6 in the AWI climate model, and recently also coupling to OpenIFS have been created, and is being used, going to be used in NextGEMS and future projects. So I think this is really a relevant model for us to have been working on. So, and I really enjoyed it. And they also make very nice graphics. That's also enough visual candy to display. What's special about FASOM is the unstructured mesh, I would say. So the local mesh refinement is really the key strength of FASOM, I would say. You can refine the mesh along coastlines or through narrow straits. You can also look at sea level variability and have a local refinement to, for instance, resolve eddies. You see that there. That's a storm, or that's the XR grid where you see a local refinement along the Gulf Stream and also in the Arctic to have a good ice influx resolution, I would say. So in the vertical, it uses arbitrary Lagrange and Eulerian vertical coordinates, so they can handle sigma layers and geopotential layers in one source code, basically in one in the same loops. And FASOM displays good parallel scaling. As you see there, that's the storm test case that I will describe later. Actually, I've been using it extensively, and it scales up to 30,000 cores. You see there at some point the SSH solver, which needs collectives, I guess, and the sea ice start to spoil the party. Sea ice because of the load imbalance. But yeah, that's a lot of effort, I think, has been invested in making FASOM scale well at many cores. So if we look at the performance landscape or the profile of FASOM, about 40% is spent computing tracers, advection, and diffusion. Another 40% is the dynamics, the momentum, and then the CIs and the SSH are quite small, but again, at very high core counts, they dominate this picture. Currently, there are two tracers, temperature and salinity, but while discussing with the FASOM team, they said, well, in the future, we will add ocean biochemistry tracers, and this number will explode. And this will mean that the application will be completely dominated by tracer transport. So that's why we agreed to handle the tracer transport and try to accelerate that on GPUs. And then within the tracer transport, it was actually the flux-corrected transport that was really the slowest, the dominant routine you see there. A simple sampling trace. The discretization of FASOM consists of an unstructured mesh where variables are either on the nodes or on the faces or on the edges. So many loops in FASOM are either over. So all the loops are either over those concepts. The memory layout. So now I'm getting a bit technical, so to say. Is vertical is the fast index, and then horizontal. So all the loops are horizontal loops, and the inner loops are the vertical loops in this code. That's how it's structured. And this is then how we envisioned the porting of this type of loops to the GPU. We say that the inner loop, which is like maybe 50 to 100 size, will be mapped to the GPU threads, and the outer loop will be mapped to the GPU thread blocks. And actually, we tested this for the this tracer or this flux correction function. We ported all these loops to CUDA kernels, and we saw that many of those kernels, as you see there below, they approach the peak memory bandwidth of the card to about 70% or so. So this was an indication that the algorithms themselves are actually suitable to lay out on a GPU. This yielded a 20% speed up of the full tracer transport. Basically, the flux transport or the flux correction method was more than 100 times faster and vanished completely out of the trace. But the solution was not portable. The FASOM team does not have developers to maintain CUDA code, and it's then also a separate code base that you have to maintain. So not ideal, and it also meant a very large effort for a small code section. So the idea after that was to leverage a different technology, OpenACC, with the same philosophy in terms of parallel layout, and use the gang loop for the horizontal direction, and the vector loop for the vertical direction. And still, although this is slower than Barracuda code, still you get a significant speed up for the flux corrected transport, and you get a much more portable solution that can be supported by the development team. And basically, in a few months, we extended this this OpenACC effort to the full tracer transport. So the full tracer transport is much more than the flux correction routine. You see here an entire pipeline, which is actually not complete, but all of these blocks consist of big loops that have to be annotated with OpenACC. And the philosophy we had is to be minimally intrusive in the first round, basically. So almost no changes to the actual Fortran code. We only take care of the parallel layout and the data movement between the kernels. We minimize that. Then we did some efforts to mitigate data movement using asynchronicity in OpenACC. Okay, great. And with some tuning, and we also enable the MPS daemon, so that's something technical. And then here is the Storm test case, 5.6 million vertices. This corresponds to like a 10 to 3 kilometer grid or 0.1 degree, 47 layers. I don't have to explain the hardware Jewels booster. And what we see is a twofold speed up for lower core counts of the tracer transports, a little bit more than 2, but this speed up kind of deteriorates when you go to higher core counts, as is often seen in ports. The GPU doesn't have enough to do. In combination, this is partially true, I think, also in combination with the naive porting being not ideal for GPUs in this case. And we see a small increase in performance of the overall application, which also is nice. Okay, let me wrap up. So, in principle, FASM2 data structures are a good fit for GPUs. OpenACC seems like a good solution for the team to continue with. The naive OpenACC gives a factor 2 speed up for the tracer part. But if you really parallelize towards climate enabling simulations, this kind of levels out again. Yeah, in terms of the full application, the partial port has limited effect. So I also have an outlook. I have a wish list. First, I think you should look at kernel optimization to see where you can get with optimizing the current port. And Atos has kickstarted this already in the flux corrected transport. They have used a mask or conditionals and could leverage collapses to increase the utilization. So you need to validate results, of course, or that's I guess speaks for itself. And then extend the naive or the OpenACC effort to the full code. Yes, there are also things like CUDA where MPI GPU direct. We didn't use that, but you have a halo exchanges in the routines, so that could be very useful to exploit that. And finally, there is an currently there is an OpenMP parallelization effort. So the team needs to think about how to merge OpenACC with that effort. Without all the code growing too difficult, I would say. So that's what I had to say. Thanks.
So we have one question from my side. Okay, another. Okay, so I started reading the question from Christian. Yeah, Christian.
Yeah. In the OpenSCC slide, you mentioned about a 7 speed up, but do you know how? Well, when you tell me how many cores is against this speed up, so it's against one single CPU core or against
No, it's the node-to-node comparison.
Node-to-node.
Yeah, so.
And it's one GPU against all the
it's Jules Booster. We use all
it's
four GPUs per node.
Okay.
Yeah.
So, okay, because it's for me it's a small speed up using the 4 GPUs. So
yeah, I agree.
I was a bit surprised.
Yeah, I agree. I think more work needs to be done also for the tracers. And this is really will entail looking at the Fortran code, and especially I think the bounds of the inner loop that prevent collapsing and a more efficient utilization of the cards. So I think working with a mask or with conditionals could really speed up. And so Ethos has done this for this single routine, and they can achieve factor 100 speed up. So if you can extend that effort to the full tracer, then I think would be much better than a factor 2. Yeah.
Thank you.
So I have just one question. In one of the first slide, you showed the scalability plot comparing several parts of the model, and it appears that the SHA solver does not scale as well as the other part of the model. So my question is, if the FESUM does exploits any external numerical library such as PSC or some other things like that.
Yeah, I would like to pass this question to the FESUM core developers.
We do obviously. We do. So we have now subcycling technique also implemented in the meanwhile. The results here were relying on a PAM solver. I guess it was from Australian. We also tried PETSI, and recently we have coded our own, which is really efficient with in combination of OpenMP, so you reduce the communication.
Okay.
So basically now the results are much better. I guess this is the results from 3 or 4 years ago. This paper.
For scale, we didn't repeat the scaling with our own kind of native solver written in Fortran because that's the PARMs, right? That was with PARMs, but yeah, might be that they are better, but we didn't have time yet to look at the solution.
The problem is that it requires global communication, and with the increased amount, of course, I mean, you need to overcome. So OpenMP is the solution here. I mean, you need to go to hybrids and parallelization here. To have efficient hybrid parallelization, then it's okay. So, but yeah, that's what we did. I guess now as a standard we have our own, which is a hybrid.
Okay.
Supportable.
So we have another question from Milan. Milan is here.
Yeah, I was just wondering, given that you said that the transport problem is mostly memory bound, I would assume that you could actually get large improvements as you already run on GPU once you go down to single precision or even half precision. And so I was wondering whether you've considered that.
Yes. Yes, we have person allocated for testing single precision. Starts this year.
There you have your answer. Yep.
Sorry.
No. I didn't know. So.
Okay, thank you again. Thank you. Yes.
Now we have Christian Guzman from BSc we are shifting to the atmospheric chemistry with a GAMP first GPU solver, a solution to accelerate chemistry in atmospheric models.
So I'm Christian Guzman from the BSc, and I will present my favorite CPU solver on the CAM module, which is basically basically a collaboration work. There's also some contributors that helps me, which is Matthew. Matthew is from NCAR, Udiol, Carlos, and Kim Saraday. This is a brief introduction to the team. Basically, from the Earth Science department, I'm from the performance team, which we aim will provide HPC service to find main bottlenecks of operational models. And as a background, I will make a very simple definition of an atmospheric model to put a context. Atmospheric models are a mathematical representation of atmospheric water, gas, and aerosol cycles. In the image, we can see the representation of the atmosphere. Basically, the atmosphere is divided in many small points that we are referring to these points as grid cells or simply cells. And in each of these cells, there are multiple physical and chemical processes occurring. So, for the atmospheric model part, this chemical process, the part of the chemical process, can take up to 80% of the time execution. So we will focus on this part in this work. As a state-of-the-art introduction, I will mention the KPP GPU chemical module. The kinetic preprocessor is an analysis tool to solve chemical mechanisms using Rosebron methods. This is widely used in the atmospheric community, so I'm taking this as an example for this reason. And this is the GPU version for the EMAC climate model achieves up to 20 speed up against the CPU single core and 186 against 2 CPUs. In the left and the right image, we can see the full table with the speed ups and the comparison. So we'll take this as a reference. But we are actually working with another different module, which is CAMP. CAMP is a newly chemical module that also has the same objectives that KPP, that to provide some flexibility to the users to configure some different chemical mechanisms and some different type of reactions. It has the advantage of, apart from computing a typical gas phase reactions, it also can compute the aerosol reactions. And the idea is to be it's a chemical framework to include the CPU solver and a GPU solver. And our objective is to focus on developing this GPU solver. Previously, to present the GPU implementation, I have to take a very fast view on the CPU solver. Basically, CAM used the backward differentiation formula from the CBOT package, which is basically a solver for ordinary differential equation systems. And this BDF algorithm requires a linear solver package. By default, it uses the Kelly algorithm for the CPU execution, while it also has a CUDA version of the conjugate degrading algorithm. In the image, we can see all the modules and packages in the same part. And for the implementation, I will call our GPU parallelization strategy block cells. Block cells basically assigns each atmospheric cell to a GPU thread block. So basically, it uses as many threads as chemical species. We can see in the right image that the traditional approach, usually for the GPU part, for example, the KPP GPU or the MPI part, maps one GPU to many threads. The asterisk means many threads. This produces as many threads as a number of cells. While the atmospheric model, in fact, has many chemical species that can be mapped to multiple threads. So basically, our block cell implementation is to map each cell to a thread block and each chemical species to any threads. This allows a higher occupancy than traditional approach, so we have more cells computing data. And in the linear solver part, we already tested this strategy, obtaining 34 speed up against CPU single thread, taking into account also the memory data movement and all this part. Only to remark that the communication is the data, the communication of the data between threads is only applied at the same grid cells, so it's only applied at the thread block level. And this is as an example, for example, in the solving of the algorithm, a thread can trigger an error because it has a negative concentration. So how it is treated? The error is shared between the other threads in the block by using the shared memory of the GPU. On the right, we have an example, very simple image of using the shared memory. So I will continue with the test environment. With the hardware, we use the CT power cluster from the BSC. It has basically two CPUs power 9 with a total of 40 cores per node, and 4 GPUs NVIDIA Volta. For the software configuration, the table, there are the two different tests. Basically, is in the CPU and the GPU. For the CPU, we use 1 and 40 processes. 40 processes is the maximum processes of a node. And for the GPU, we launch as many threads as a different chemical species. So it's basically the chemical species of a system per the number of cells. Then there are also some common configuration. For example, we are translating the main loop of the backward effectation formula. So we are not translating previous initialization, so like, for example, calculation of the DT or something like that. And for the chemical mechanism, we are testing a gas phase chemistry, carbon 5, with 166 species, and the number of cells 100 to 10,000, and with a tolerance of 0.01%. So for the results, this is the speed up. Well, we have up to 35 speed up in average versus a single thread execution, and with a standard deviation around 2. The standard deviation is produced mostly because we are using different approaches for the linear solver. One is for the CPU is a DDEC solver, while in the GPU we have one iterative solver. So the small noise that can produce the different solvers can produce also different iterations in the algorithm. So there's a bit deviation on the speed ups and a bit noise. And we can see in the plot that it stops scaling at 10,000 cells. And we also tested against the 40 processes, and for the 40 processes we have the 20% more faster than the 40 employee processes. We are using only one GPU, and also there's a lot of communication and there are still some optimization work. We also estimate that using the 4 GPU we are around 4.8 speed up. It's an ongoing work, but at least we can say that only a single GPU it's better than the MPI execution. So this is an achievement for us. And we also make a kernel profiling of the application. We make some optimizations, like for example, adjusting the number of registers per thread to an optimum number. This register usage is likely preventing the kernel from fully utilizing the GPU, which is basically this usage is mostly produced by algorithm definition, since we are computing big data like the Jacobian matrix. In the right, we can see this image. We'll take it from the CUDA profiler tool that remarks a block limit of the block limit as our main bottleneck. So we have still room to optimization. As for the conclusions, our block sales strategy increases the GPU parallel threads against traditional implementations, which are number of threads equal to number of cells. the CUDA implementation of the VDF loop performs up to 30 times faster than the CPU single thread, which is 1.2 speed up against CPU using the fully resources node. And since the lot is independent between threads, we estimate up to 4.8 speed up with the 4 GPUs per node. The kernel profiling suggests also a limitation on the performance by a memory. And our approach can be used in more chemical applications thanks to the versatility of the CAM module. As a future work, we want to add the multi-device functionality to compute up to 4 GPUs per node. We also want to balance the load between the CPU and the GPU architectures, since we have the CPU and the GPU solver, so we can launch both simultaneously by dividing the load accordingly, and also integrate our implementation inside an frame model to make a more longer simulations and more tests. So that's all. Thank you.
So thank you, Christian. So we have one question from Kim.
It's more if you could elaborate on what you were developing with CUDA, if you can explain to the audience how is using CUDA. I wanted to bring this topic because I think at the end we will compare the different methods used during the session. So you are the only one that I think you are approaching with CUDA directly. So if you can comment, please.
Basically, we are working with CUDA because it's there's a lot of complexity on the code. I mean, we are not translating only a single loop of reactions or a double loop with a matrix. We are translating the OD solver algorithm, so it's a more complex. We are computing chemical reactions, so it's a bit harder to do with WinOpenSCC and the transformations. And also, we want to maximize the performance. So we don't know exactly how OpenSCC it's modulating the kernel node, making the computation, but with CUDA we have more control and we can maximize this performance. Basically for performance and because it's very complex.
And just to complete the question, and what about the maintainability of the code? I mean, are not HPC experts able to maintain the code with this approach, with the CUDA? If the chemical expert want to add other feature to the model.
The code?
What do you think about?
Depends. It depends because mostly the code to CUDA, well, it's for the part of the initializations, no? Like, I don't know, translating moving the data to the GPU, or adapting the initial data to a matrix adapted that it's that can be useful for the GPU, but for the main kernel, it's the same code that the original. So there are not like two versions of the CPU GPU. It's only at least for the main, for the main scientists. If you want to add, I don't know, something in the kernels, you can.
Okay.
So it depends, no?
Okay. Are there any question here?
If I only ask on this, I would say that it's quite difficult because we'll need to find CUDA developers, and even if in the team we have Christian that is doing a great work, but if you go, I think, to the market and look for CUDA, really pure CUDA developers, I think it's really hard. And
I think that the scientists should. I mean, it's in my personal opinion.
Be careful, I know.
No, but shouldn't focus on this GPU implementation. No? It's like you have to have an expert on CUDA, but maybe if you translate this to OpenSCC, you need an expert on OpenSCC.
Yeah.
So there is no much difference. No, it's like understanding CUDA, understanding OpenSCC, understanding OpenMP. Maybe there's a more lines of code with CUDA, but I think that the CUDA implementation of the GPU should be like a black box, no? That for the scientist part, no? And you should test this the configuration, the part, the chemical reactions, and then the GPU expert can test this OpenSCC, this CUDA implementation, and then focus on the performance. This is what is our objective, to achieve the maximum performance, and CUDA is currently one of the best options to achieve the performance.
Yeah, but you still need CUDA developers.
Yes.
There is a comment from Gijs.
Yes, I have a question about load imbalance. So you use this ODE solver, and is it because of load imbalance that because it iterates and not always on the same, it doesn't stop at the same point? So is that the reason why the mapping from grid cells to threads is underutilizing the hardware, or is it just another reason?
What do you mean do you mean that we are mapping these threads because load imbalance?
Yeah.
Well, it's more to use more threads simultaneously, not.
Okay, so it's just a matter of size. Yeah.
Yes.
Okay.
It's more like, well, I can go to the. Did you remember the kernel profiling that highlights the bottleneck on the registers on the memory? Basically, if we use the traditional implementation of one thread, one cell, we didn't have to. In each thread, we need to have this all the chemical species. Yeah. So we are using more registers.
Yeah.
So if CUDA designs that each thread has a number of registers, if we are using more, then we can't launch more threads, because we are limiting all the registers to a few number of cells when we can launch more threads. So basically, the idea is that.
Okay, Luis, do you have a question?
I have a question. So I really appreciate that you look really down to the register level. That's quite nice work.
The microphone. Oh. The mic.
I really appreciated your work that you looked even down to register level. But unfortunately, my production platform has a Xilinx FPGA. So I'm totally pissed off with a CUDA C++ or a C version, or I get only 10 million billion units or hours on Lumi, which unfortunately has an AMD GPU. No CUDA. So do you think it's a sustainable model?
It can be translated to FPGA in the future if it's needed. I mean, we want to explore also some. It's not like we are moving to the rubbish this OpenSCC, OpenCL implementation, no? Because we also want to test an OpenCL implementation that precisely for this, no, for this FPA or AMD NVIDIA's. In fact, in the Proxima Minor 5 we'll have AMD NVIDIA. So we want to also focus on the heterogeneous part, but for the moment we will focus on having the best version of the code, the optimizing version, and then we will focus on the FPA portability, on the portability part, FPA, AMD, etc. I don't know if I asked your question. I answered your question. So.
If I may react only, we still don't know how will be Mare Nostrum 5, so nobody knows.
In the AMD conference, they send an email to PDF that we will have AMD.
But nobody. Let's say it here that there's not official take.
Okay.
And then also I understand your concern, Luis, that once you stick with CUDA, this could be. But that's true that at the beginning it started also as a decision that we had this machine at home, this Power 9, and we decided to move to CUDA, and that's now a big concern on what to do. So on how we will move. We can explore many of the alternatives that Christian mentioned, but that's true that once you take a decision, and probably at the beginning we took this decision because what we had at that time, that it makes or it will fix a lot your development path.
I mean, the development could be sustainable if you can keep the people who learned all the details and pay them accordingly.
Yeah.
Then it's sustainable because they can, if they do the work the second time with a different runtime environment or language, that's totally fine because then they are 100 times faster than in the first run.
Yeah.
But that you need to take into account. And if you have educated people who can do that coding, you have to compete with industry.
Totally agree.
And then you're really in a mess.
That's why at the beginning we started with, I mentioned this idea of finding CUDA developers, which is not really easy. And so, yeah.
Anyway, only to I just arrived, so I don't know. But something good about this, because we took this decision at the beginning also because the machine, but the point is the approach that Christian is following, this block cell, this chemical instrumentation of the library, is totally independent of the paradigm that we are using. So we have to move for another one in the future. It's no problem. Because, sometimes the solution with NVIDIA are very dependent, but in this particular case, it's only moved to the code to another one, and the approach that he is following is exactly the same. So we sleep very well about this, so no problem.
I see one hand raised by Erwan.
Yes, thank you very much for this presentation, and thank you, Mario, because you, answered the question. Yes, my question was, is the approach generic enough to be independent, and you can think about having like a description of the paradigm or the approach and then generate any kind of optimized, even if this may be less performance that you will do by hand as a first guess, but so the answer is yes. Thank you very much.
Okay, last one. Yeah.
Have you considered using COCOs? Have you thought about the feasibility of implementing the code in COCO so that you wouldn't have to worry about the architecture that you're running on?
No, sincerely, I don't check the COCO implementation.
Because it's Fortran, so we can...
Yeah, but COCOs has...
yeah?
I mean, Icon is also Fortran, right? And you said that you were exploring COCOs for Icon.
Yeah, but that would mean also rewriting it to C++.
Yeah.
Okay.
So it would be very nice to have something with COCOs, and I know that for your previous experience, you have been working in COCOs, and they are nice. And I think that probably in the next talks we will have something from our US colleagues, but yeah, right now we cannot use it.
Okay, so thank you again, Christian. We can break here and reconvene at 4:35.
1 or 2 minutes before 35,
Yeah, okay.
so that we start at 35. Thank you. reconvene. And we have Michael Lange, I hope I pronounce correctly, from ECMWF, that is going to talk to us about preparing IFS for HPC accelerators via source-to-source translation. And I will tell you 5 minutes before the 20, so that after that we have still 5 minutes for the questions. Okay, thank you.
Cool. I'll try and make that. Cool, thanks. Yeah, hi, I'm Michael. Sorry I can't be there. I work at ECMWF and I run the Hyper24 project, which I want to talk about a little bit about first half of my presentation, and sort of focus on the source part and that we use to prepare IFS for HPC accelerators in the second part. So to motivate this, talk, I usually like to go to Niels's wonderful runs, and they did a few. Niels and his team did with a few years on Summit as part of the Inside project, and these 1.4 kilometer horizontal resolution runs, which sort of set a new benchmark in terms of the science, new challenges in terms of adopting the model to the when you resolve processes, and sort of a whole bunch of scientific changes that are needed to actually sort of reevaluate and things at that scale. But it also, for sort of HPC architects and sort of HPC optimizers like myself, it puts a real challenge in here, because as much as these runs produce wonderful pictures and visuals, they're nowhere near fast enough yet to actually fit into an operational window. And this is sort of the grand challenge for us for the next coming years. Can we get close to sort of operationalizing these incredibly high resolution runs? And obviously that brings us to the Destination Earth initiative, which is targeting, amongst other things, the high performance aspects of some of these runs, and designing these highly accurate digital twins. And for us at ECMWF, it also comes with access to these large Euro HPC platforms. And as we've already heard yesterday, the Lumi system and Leonardo coming online later as well. These sort of pre-exascale systems have very large GPU partitions, which makes them powerful. And that's sort of the general motivation for why we want to adopt the IFS to these accelerators and to fully use these. Now, this brings me to Hyper24. Hyper24 is effectively an internal project to ECMWF that is looking at adapting the IFS to accelerator-based HPC architectures in general. This is because it's something that we've always wanted to do. This was always sort of on the cards, but with the Destination Earth initiative, it obviously gets accelerated, and we give it more resources and access, etc. And the vision and sort of the grand idea behind this project is that we want to rewrite and sort of refactor the IFS towards a accelerator-enabled multi-architecture IFS. And what I mean by that is that we don't just want to take like a fixed version of the code and sort of put a few OpenACC statements around a few loops and sort of have to do it all again in a few months when the next release cycle comes along. But instead, we want to see how we can change the code, the infrastructure around it, to sustainably keep developing these technical layers of obviously, right here, right now, GPUs, but accelerators in general, and these accelerator capabilities alongside the scientific development to effectively future-proof the code in a sense. Now, this is motivated obviously by the fact that this heterogeneity that we see in the hardware space is not going to go away. We're currently talking about GPUs, but in a few years, we'll be talking about 3 different styles of GPUs, as well as 2 different non-GPU accelerators, 3 different styles of CPUs, etc., etc. So we need a way to deal with this stuff more flexibly, and this is sort of the idea behind this. The other consideration is that the IFS, possibly more so than other codes, is very heterogeneous in terms of the computational characteristics under the hood. So the components of the IFS themselves vary vastly in terms of how they stretch the machine. For example, the spectral transform die core is limited by the latency in the global communication of the all-to-all of the network, whereas things like the physical parameterizations have no communication whatsoever, but really stretch the cores and the raw pure compute, whilst things like ocean and waves are memory bandwidth limited, etc., etc., etc. So the idea behind this is that this process will be will take time, and we want to incrementally adapt component by component the model, figuring out the recipes for this in a sustainable fashion so that we can effectively adapt to future hardware developments much more flexibly, and sort of effectively develop dedicated sort of GPU or accelerator build modes as part of the cycle, and maintain them and test them and sort of curate them as we move along. this brings us to the big challenge here is if I want to adjust the IFS to GPUs, how do I make sure that the CPU performance isn't impeded, that we still run as fast on the operational runs as we run today? And obviously, this is because at home we still have a CPU machine. And this brings us basically, it's a sort of separation of concerns sort of message. How do we deal with multiple programming models in a single code? And how do we shield the day-to-day scientific developers from the impact of these changes, of these technological changes onto the day-to-day workflows? And there's sort of three fundamental software engineering principles, if you will, or sort of three pillars that we're aiming to follow. The 2 points in the middle here, sort of the same thing. The first one being sort of use library interfaces as the mother of abstraction. If you can and have a fixed library interface and you have a component that doesn't actually change in the day-to-day science workflow, you can behind a clean library interface do a lot of stuff. You can actually have quite vastly divergent code paths. And in your experimentation, in your adaptation to different types of accelerators and hardware architectures. In a similar fashion, moving closer to the day-to-day code, flexibility of data structures, instead of letting the Fortran runtime deal with every array implicitly, using field objects and sort of imbuing them with utility methodologies to manage and marshal the placement in complex memory hierarchies, moving on and off the device, etc., trying different data layouts, etc. Similarly, control flow, same story, trying different looping strategies, combining them with the data layout strategies, etc., will allow us to effectively explore these various recipes as time progresses and as sort of hardware evolves with every generation. And finally, we get to the source-to-source, which is actually to the part of the computational kernels that really, where you really have to change the math, the arithmetic kernels in the looping strategy. And when you have things that effectively impede CPU vectorization, you will slow down the CPU. So you can't actually commit this to the source, and instead you encode it and apply it in an automated fashion via source-to-source. So before I get to the source-to-source, I'm going to have two small little examples of the first two principles. So EC Trans, already mentioned earlier by Willem and by Sam and by others, is effectively a newly released open source spectral transform library that we've made available on GitHub, which is effectively a sort of cleaned up and neatly packaged selection of spectral transform routines. Some of them, it's effectively the stuff that was used in these summit runs, and just nicely packaged now. There was a lot of work in sort of modularization and sort of cleaning some of this stuff up to release this alongside a sort of minimum requirements and utility library called Fiat. And this makes interaction with collaborators and vendors easier, and it's nice. And obviously, I wouldn't be mentioning this if we didn't have at least a sort of prototype GPU-enabled version available on there as well. It's in a branch, big blinking warning lights, still work in progress. Not all features are supported yet. So much more to come, and sort of before we are fully happy with this. But we already have GPU-enabled NVIDIA branch there, Fortran plus OpenACC plus vendor-specific libraries for FFTs and BLAS. Good scaling behavior. Now also with CUDA-aware MPI, we actually see a nice speed up here on Joule's booster from that. So we're quite happy with it, and there's more to come. For example, OpenMP5 support, etc. The next point that I mentioned was these flexible data structures. Here we sort of have this in a two-stage approach. The first one being what we call internally the field API. It's really just a small sort of Fortran 00 set of classes that encapsulates the concept of a field that can wrap around existing data structures, understands internal data structures of the IFS, and sort of can add all of these little utility routines that you need, like moving to the GPU device or coming back to the host. Key thing is, if I have a custom API around this, I can hook this into the OpenACC runtime, but I can also later on develop hooks for the OpenMP runtime. So I'm sort of, again, just hiding the technical difficulty from the day-to-day programmer who knows that there's something going on with GPUs, but doesn't want to know about OpenACC and OpenMP. Obviously, the long-term goal here is a much more comprehensive solution of this would be Atlas, and we've had Willem talk about this earlier, which is a great library that on top of sort of GPU support brings generally data structures for numerical algorithms, remappings, interpolations, and operators, etc. And so this is sort of where the long-term where we want to go, but we have an intermediate sort of staging API that we can use in the meantime inside the code, because refactoring is hard. And with that, I actually do get to the source-to-source translation of the physical parameterizations. And what I can introduce here is an in-house tool codenamed Loki that is a programmable source-to-source translation tool written in Python. And the key idea, again, is exactly this. For all the optimizations and the transformations towards GPU optimization that will have a detrimental effect on the performance of the CPU, I cannot commit them to the source code. So instead, I can encode them in what effectively becomes a really complex preprocessor. And I can apply them in bulk to large sets of files as part of my build process. So the way this works in Loki is that Loki doesn't actually need to see the entire code. It's actually configurable and has a sort of auto exploration feature where from a root call, it can basically follow the call tree and sort of isolate subcomponents of the code, and then it will go through all the files, parse them with the front end. Again, thanks to the SDFC guys who maintain our absolute favorite function, the F parser, just like PSyclone. And what Loki then does, it exposes basically an IR, an internal representation, a tree of Python objects that represents your code. It also presents you with a bunch of utility routines like visitors and transformation utilities to effectively write your own transformation. That is sort of the key thing, that the actual power and the responsibility lies with the HPC expert, the user of the tool, to write the transformation that takes the code from the current state into the state that you want it. Once you can then write that back out, and you've played as some neat little injection mechanisms that sort of replace the entire subtree. And that allows us to effectively develop these aggressive performance engineering optimizations that sort of can go counter to traditional CPU vectorization without the scientists actually being exposed to them. We can still apply them at build time and compare that we're like for like in the runs, etc. We can also exploit alternative programming models with the C backend, etc. That sort of thing can be done, which is more sort of on project level, where we've played with other things as well. So just for the sort of code gen nerds in the audience, just a very brief look under the hood. The key thing about Loki's internal representations is it's actually 2 levels of trees. The sort of control for one is custom to Loki, so it deals with things like subroutines, conditionals, intrinsics, loops, or assignments. Very importantly, however, the actual tree of sort of symbolic expressions, so the right-hand side and left-hand side of an assignment, we actually use an external tool known as Pambolic, which comes out of Andreas Klockner's CodeGen stash, which is really great and free and open source on GitHub. We enhance it with some sort of quality of life and sort of syntactic sugar. But it also means that for our visitors and iterators, we have a choice of actually dealing with the entire tree, which is really complex, or for certain lookups, we actually can just deal with a high-level tree, which is the way we sort of manage complexity. And what it allows us to do is then build APIs like this. So a visitor like this, find all the nodes of type assignment, visit the body of this routine, and we'll just run through this, ignore all the blue symbolic expressions, and just find all these assignments. This brings me to a little example of what the actual API looks like when you write a kernel that transforms something. So suppose you have a subroutine and you want to remove a particular set of loops. Say vector loops are always denoted with the loop induction variable I. So what you do is really quite simple. You create a map, just a simple Python dictionary. You use this visitor API to run through all the loops in the body of a routine. And for each loop, you then check the variable. We have, as I said, some syntactic sugar here that will basically make case-insensitive comparison to a string. So if that variable dimension here says just I, it'll match, it'll take this, and you can then sort of map just the loop to its own body. This in itself doesn't do much yet, but once I feed that map of all the loops that have this particular variable into a transformer, and I visit this routine body again, and Loki will effectively rebuild that tree, only replacing each instance of that loop with its own body. Thus, you basically strip the outer do and do part of the thing. You still have to deal with the indices of I later on in the sort of loop body, which is sort of the stuff that I don't put on the screen. But this is sort of the high-level API that we can support. The key point, however, to take away from all of this is that in this entire tool chain of processing Fortran files, the various pre-processing front ends, and creating internal representations, that part, the transformation from one style of code into another, is left to the user. So this is left to the expert. You need to know what your code looks like, and we make no assumption about generality. You can write any sort of super general transformations or super specific. As I've just shown, I've used the fact that I know that all my vector loops, for example, have the same induction variable name. I can use that and as a rule, and I can enforce it in my model, and I can then use that for the preprocessor to effectively strip all my vector loops, things like that. So it's a sort of, you make your own recipes and you find your own sweet spot, what works for your particular model. But it's also why I do not make any promises about other models other than IFS with this. Yeah, because of this, I effectively, the key
5
thing to notice
minutes.
then really
Sorry, just 5 minutes, just to give you an indication.
Cool, thanks. Yeah, so this is actually the last part of my talk. So because of this sort of with great power comes great responsibility thing, the key thing is to actually understand your code and what you want to map to what for what particular architecture. And so here I'm just going to try and walk through one particular feature of the IFS grid point code that we're trying to use with this. And this comes back to the original sort of thing that Valentin Clément and the original Claude developer had with this idea of a single column abstraction. The fact that in all of these grid point codes in NWP, there is no data dependencies in between columns, for example, in the physics. So we have a lot of free parallelism. And the key thing to note here, where this is sort of where the diverges from the Claude principle, is that in the IFS, we actually have a very bespoke memory data layout. And that is that we use blocking, not just in the loops, but also in the data. So the x and y axes are resolved, so our columns are just organized in one flat array. But this free parallelism in the horizontal dimension is actually used in two places in the allocation. One on the innermost, which is sort of the green box on the left here, which is used for vectorization and sort of aligned memory axes. And also on the outermost, which is the block index, which is used for thread level parallelization effectively. The other curious thing about the IFS then is that we also co-allocate fields. So the idea that, for example, U and V and T and A and I and all these variables, they all have a unique ID and are the second to last index in that particular scheme, which means when I resolve the block index, we have, for a particular set of blocks, we have all the data closely co-allocated of this working set of variables closely co-allocated, nicely packaged for the caches on CPUs. But all the data of U, for example, is actually distributed across different chunks in memory. And this is what works really well on the CPU, which is why the IFS has scaled for many years since the 80s, because it's a very, very powerful mechanism. And the realization is here that we're using this free parallelism in a two-level scheme. Outermost OpenMP parallel with threads, innermost vectorization in the classic way. The fast loop is the innermost, so even if I have a vertical walk through that column, the computation always is wrapped around this vector loop on the innermost. Now, the key realization, though, is for us, and this is sort of as really diverges from the Claude, is that we can actually use this two-level of parallelism in the GPU itself. This is similar to one of the speakers just before me, where we basically separate this between the OpenACC gang loop and the vector level. And we're using the same trick. So after we localized our data into the device memory, and as I said, I have a bespoke API to do this, so I can actually do a little block style pivot so that my U is still block allocated, still has block index, but they're now contiguously allocated because CUDA pointers like contiguous data better. And I can still use this outer index to resolve my block loop. Do this at the gang level, which distributes this across DSM, the streaming multiprocessors, so that all these data accesses are nicely aligned. So I'm feeding it in the same sort of style down the cache pipeline, just inside the device. The key thing now is that I need to vectorize inside, and this is where the difference between GPUs and CPUs really kicks in, because you're doing SIMT for threaded on GPUs and SIMDs and multiple data on CPUs, where effectively you need to invert this loopness. The vector loop that was previously innermost now needs to go outermost, so I need to flip all these loops. And this is the old Claude trick. Inside the kernel, we're doing exactly the same thing as the Claude did. We're marking it as routine. We bring the vector loop outermost as much as we can. We're marking sequential innermost loops, the things that aren't parallel, and let the compiler deal with the rest. And this works really, really well. So we've demonstrated this on CloudSC. Again, another open sourced dwarf for the dwarf open sourcing. There's a great article, by the way, in our ECMWF newsletter recently. It's a standalone version of the Cloud Microphysics. It has representative parallelism memory layout schemes. And it's really challenging to optimize. That kernel actually really challenges the compiler because it has incredible high register pressure, and is really our sort of acid test for new compiler architectures. And what we can do with this is actually do a comparison not only across compilers and hardware. We can also look at different looping and data layout schemes. What I've shown here is this Loki SCC. What I had in pictures, there's Loki Claw, which didn't work too well for us because of the blocking thing. I compare to sort of the best optimized Rome CPU that we have right now. There's more aggressive optimization that I can do with this, where effectively my OpenACC code now really looks like CUDA, with sort of single scalar accesses inside a warp style loop, which gives us another big boost, which we've explored with, but it gets really hard to drive this through a large chunk of code with recursive calls, but we're working on it. And yeah, last point I want to say about this is that you use CloudSC quite routinely now to compare hardware. So we have an Intel CPU, AMD CPUs. We originally developed Loki for an FPGA. So we have some FPGA numbers. We have Volta-style GPUs, Aperture-style GPUs. We have a SYCL version of it with a C backend. Again, I can sort of translate into C flavors with Loki as well if I need to. It's a bit more brittle and not quite as mature as the rest, but it's there. It can be used for exploration. And with that, I thank you for your attention. I'll leave you to read the sort of conclusion and the overview for yourself and take any questions. Thank you.
Yes, thank you, Michael. We have one question from Kim.
Yeah, thank you. My question if Loki is ready to be used outside ECMWF, and if so, which development skills you think that are needed for a user to work on Loki with Loki?
So for now, it is in-house. We're obviously happy to sort of share it with all sorts of with any collaborations, be this via European projects or Destiny or things like that. I'm happy to give access to member states at any time. Be aware that it is sort of beta stage at best. Like not everything is working as smoothly as it always needs to. There's only so much daylight in a day to fix all the bugs. But it is pretty comprehensive. You can give it play. It does help if you understand a little bit of compiler theory and have done an undergraduate CS course. But it's not strictly necessary. But it does help if you know trees and visitors and that sort of thing, because it is, in the end, all DSLs and source to source are effectively mini compilers. So yeah, it's definitely more for the CS and sort of HPC oriented people. But yeah, it's not like you can't learn this.
Okay,
thank you.
Are there any further questions?
Yes, hello. I have a question for like a practical use of Loki. Do you think it could be used like to like swap arrays in force one code, like not necessarily generate OpenACC or a code, but just use it to change the layout of the array access?
Yes, that's exactly what it's used for. In fact, that was sort of the point I was trying to get across with the description of the vectorization. The key, whether you annotate this with OpenACC or OpenMP, is sort of almost a secondary consideration. You need to get the mapping right, but it's the flipping of the loops that's the important bit. It's the flipping of the loops while you're not doing this with like regexes and grabs, but while you're using a sort of proper source tool to properly do the analysis and the transformation stage. And that's exactly what Loki was built to do, flipping loops and promoting data and promoting variables. That's effectively sort of bread and butter stuff.
Okay, Gijs, do you have questions?
Yeah, I was wondering about the sustainability of this solution. So suppose you have all your physics packages and a whole bunch of Loki recipes or scripts, and the scientists can alter the Fortran code, and somebody decides to rename a variable. How do you track that and make sure that everything keeps on working? Is there some kind of policy for that? Or?
The short answer is testing. So yeah, the key thing for Loki is that it's not necessarily, unlike things like PSyclone, high-level DSLs, it's not actually meant to sort of make your life super easy. It is meant to not make your life much worse. It does impose additional rules. So as I said, I can make up the rules about variable naming, etc. And if you diverge from that, yeah, things will break. And I will need to pick this up with a CI test. So every change that posts, once you have a Loki recipe and you have it implemented in your release code, you need to test that code every commit. So that if somebody does actually use a different variable name for a vector dimension, some alarm bells go off. That's sort of, that's the thing, because with a DSL you can enforce it. With a source-to-source, you need to rely on people's good behavior and enforce it via testing from the outside. But testing.
You again, Michael. I think.
Thanks.
We can move on.
Yes, we have. We should have Thomas Hauser from NCAR on enabling large-scale modeling on GPU-accelerated nodes for NCAR's next supercomputer, Derecho. Yes, here you come. Hi, Thomas.
Hi.
So I will tell you 5 minutes before the 20, and then we will have 5 minutes questions.
Okay,
and I guess,
thank you.
Is that okay with the slides? Yes, you can start.
Okay, thank you. So I'm Thomas Hauser. I'm the Technology Development Division Director at NCAR and CISL. I'm also currently Interim Director of CISL, the Computation Information Systems Lab at NCAR. So my team, and I mean, CISL especially has really been involved in preparing science application for GPUs on NCAR's next generation Derecho supercomputer, which is unfortunately a little bit delayed because of supply chain issues, and also other agencies have priority in acquisition of the next supercomputer. So NCAR really, in its strategic plan, called out exascale and heterogeneous computing, kind of interplaying with the modeling ecosystem and also integrating with data science and AI. And so we launched a major initiative kind of to move towards heterogeneous computing. We have kind of 3 focus areas in my area, kind of the data analysis workflow, AI, and then accelerators and compression. And each of those areas provides training, education, and then working across the different labs at NCAR to really move the technology forward. So here's kind of the computing ecosystem at NCAR. So Derecho so that doesn't exist, will be delivered hopefully next late summer. Cheyenne is our existing supercomputer. We have an analysis machine learning cluster, and then we have kind of large-scale storage system for long-term data. It's all connected to a high-speed network. And then we have science gateways and data transfer services and an object store, which we are still exploring kind of what's the best usage connected to that. So Derecho has really been a change because this is going to be the first supercomputer at NCAR that has a substantial amount of GPUs. So it has about 20% of its performance will come from GPUs, 80% from CPUs, and that was chosen since most of our users still run CPU-only code, was chosen to provide kind of a compromise between the different requirements. There's a slingshot interconnect from Cray, and then using some large Scratch file system. It will be housed in our NCAR Wyoming Supercomputer Center that's in Wyoming, which is a state-of-the-art data center. Our GPU nodes are basically consist of one 64 AMD Milan processor and then 4 NVIDIA Ampere GPUs. So that's kind of, and then we have 2 nodes per compute blade, 64 blades per cabinet, 120 nodes. So this is the GPU portion of our system that's going to be delivered. We have a test system now on site. It was just delivered 2 weeks ago, and I think it's in the process to be made accessible to our users for testing and importing their applications. So yeah, we have a 80-20, as I said, split between CPUs and GPUs. And this is really a major increase in GPU capabilities. And it required for us really a major training, outreach, and support effort, and it's still ongoing to make users aware of the capabilities, but also helping the software teams to porting the codes to GPUs. So we have several teams. We have a GPU Tiger team that works more on the environment, software environment. We have this Derecho application readiness team, and then different advanced scientific discovery team. And NCAR provides at the beginning of the system, and the system becomes available, large chunks of the system for these advanced scientific discovery teams. And these teams are interdisciplinary teams with software engineers, computational scientists, and scientists to really look at a very large scale science enabled by the new computing capabilities. So one of the challenges for us is really developing expertise within the user community, converting code, especially within the software engineering community, porting guides, particularly for Fortran. I mean, I think Fortran is still heavily used at NCAR, and to use certain features, and then how do we optimize multi-node runs there. We work closely with the NCAR software developers when appropriate. We're also working within CISL on optimizing the software stack to make sure the best configurations are chosen for the hardware. And we're exploring some new capabilities we haven't tried, GPU direct storage for I/O, and then really developing over the next few months the software ecosystem and the user environment, because this GPU software stack is rapidly evolving and requires kind of frequent updates, which we haven't been doing as much as we are now planning to do. And then we're gonna try to create these user communities, sharing best practices, arrange trainings on GPU for GPUs for our user community. So that's a big effort, kind of trying to move forward towards GPU systems. And also, I mean, part of the story, I look at Derecho, our new system, as a stepping stone to maybe some of the DOE machines that are coming. I mean, looking at those, preparing for some of the inside proposals so we can efficiently utilize some of the GPU systems that are coming online. Our traditional code, CSM, WRF, basically CPU only. So we really have worked hard to explore other codes and workflows that can be optimized on GPUs. So we have a version of MPulse-A that's GPU enabled. We have FastAD, that's an LES code that's written in CUDA or accelerated with CUDA. We have MURAM, our kind of solar physics code that now works really well on GPUs. I'm not going to talk about that. We have a GPU WRF port, and then obviously all the ML, machine learning and data, deep learning workflows. And then one project I'm involved in, Earthworks, which is also to provide a high resolution coupled GPU Earth system model. Software we're going to provide is obviously CUDA, OpenACC, OpenMP, but then also other libraries and GPU direct MPI, for examples. And then kind of a whole stack of machine learning and deep learning tools. And I think we are looking actively as we're going to use SPAC. So we're going to use SPAC from the DOE Exascale project and exploring. I mean, I've been with my team going through the extreme scale scientific software stack from the DOE Exascale computing project to really look at what are the components, what can we take from there, what can we learn, and what can we reuse. So we have been using some of the FFT routines for our MURAM project, excuse me, for MURAM. And so we are looking at what software tools and packages can we adopt at NCAR to accelerate kind of the move to GPUs. So right now we are in porting and development work on our kind of analysis, and FROST is our kind of test system there. We had a call for accelerated scientific discovery project proposals to work on the NLeSC test machine called FROST. We we're working on the deployment was really delayed. The system was supposed to be here, but now it's going to be delayed. And so our early users will be in the fall of this year on Derecho. In Q1 of 23, I think Derecho hopefully will be open to all users. And then at the end of 22, Cheyenne is decommissioned. I hope that this is kind of the plan, and I hope we don't encounter any more delays. We've been doing a lot of workshops that have started in February of this year, and they're going to go through August and beyond. Materials are all open source. You can look at the GitHub site, and we really cover kind of very basic programming by GPUs, concepts and terminologies, just to bring users, kind of get them on to our system and understand the capabilities of GPUs. We've taught some CUDA classes, OpenACC, and then kind of the verification tools, the NVIDIA profiling tools, and then how you program multi-GPU and multi-node GPU programming. Most of our codes, all of our codes are really using MPI. So I think that transition wasn't too difficult, but still, how do you use that efficiently in these new GPU nodes? So we are providing training on that as well. One of the things, the main approach we've been doing is using directives. So OpenACC standard directives to achieve performance portability. We're doing a test-driven development, really trying to make sure we have a kind of continuous deployment and integration test as well, and make sure the results are staying the same. And there's sometimes challenges. We have developed some tools actually to help us if there's some numerical changes, right? Because you change of order in floating point operations. And we have some tools that do some ensemble runs and very quickly discover where changes happen. And we're gonna want to kind of explore those tools and develop those tools more. And we'll obviously do a lot of profiling to prioritize refactoring targets. And we are exploring other technologies. I think it was talked about. I mean, one of the things is OpenMP, just to look, and we are looking actually at a translator that has provided some good results in one of our codes I'm going to talk about, to translate OpenACC directives into OpenMP. And we are also looking at Cocos or other approaches. So we are doing, most of our work has been on OpenACC and has been pretty successful there. We're making sure we have the validation results, that working closely with the scientists to make sure the results we achieve on the GPUs pass the physics. And then we're looking at functions, the right functions we need to port. So part of our approach is with this advanced discovery, really to enable large-scale scientific discoveries. And one project is turbulence and Lagrangian transport in the hurricane boundary layer. And you can see the team here, John Dennis and Sherry, these are software engineers and computational scientists that work in my division. And they collaborate very closely with the PI from the University of Notre Dame and another co-PI from NCAR. So we are creating these interdisciplinary teams to really make sure there's a science case that really fits well for the GPUs, but also we have the expertise to port the code to GPUs. And you can see, I mean, the goal is really to increase the understanding of the process at the RC interface, affect kind of the large-scale transport of dynamics. So how does these interface processes affect these large-scale dynamic processes? And the approach is really through LES. And you can see a schematic here at the bottom left of kind of the hurricane. And then you can see the domain we are trying to simulate using LES, which is about 5 kilometers cubed with a 3-meter grid resolution. So fairly fine resolution in order to really capture kind of the the spray and interaction on this air-sea interface. And we're gonna basically, this is an LES code with Lagrangian droplets. So it has a Lagrangian cloud model plus sea spray model, and it needs a very large number of these Lagrangian, kind of here in blue, particles that are transported between the different grids. The base code we've been using is CM1, Cloud Model version 1. It's a Fortran code with MPI, and we accelerated it with OpenACC, and it also augmented this with OpenACC accelerate Lagrangian transport capabilities. The resolution will be about 20,048 by 20,048 grid cells with a 2.5 by 2.5 by 2.5 meter. And depending on the cases, we are estimating to need droplets in the order of 10 to the 5 to the 10 to the 9. So a large number of droplets and about 90K of GPU hours is estimated for this project, and creating 72 terabytes of generated data. I mean, this is one of the other areas. I think in this case, it's not too bad, kind of the data results. So at the beginning, I showed you kind of the data analysis and workflow. So we're working also very hard on making sure the data analysis of these projects is not becoming a bottleneck. And we've noticed in some of these projects, kind of before my time, I think 6 years ago, some of the scientists complained they got stuck now with large amounts of data and didn't really know how to process it. And in this case, we're really working closely to make sure that data processing is not a bottleneck there. And we did some benchmarking. They're still not finished. I mean, we still have some time to tune it, kind of comparing these 4 V100 NVIDIAs with 4 Broadwell CPU nodes. And we could see about a 4.4 reduction in execution time.
Thomas, 4 minutes. Thomas, 4 minutes.
Yep. Okay, I'm close to be done. So thank you. So I think this was a good case. I mean, we worked with the scientists. They really need kind of these large eddy capabilities, and it has very large problem sizes per node or device. So that's ideal for GPUs. I think the movement of particles is a good one. And really the science really mapped very well kind of to our GPU approach. The other project I want to highlight, and we have a couple of more, but is the GPU MPAS-A global convection simulations. Again, this is a mix of different labs, MCube, Sizzle, Sucrease is a software engineer working in my lab, and then the research application lab. So kind of interdisciplinary teams really driving the development. And we want to do a series of global convection permitting simulations at about 3.75 resolution to better understand the dynamics of tropical convection and the predictability of atmosphere in different climate zones. And then we plan to assess added value of convection permitting resolution in simulating structure and life cycle of mesoscale convective systems across different climate zones, capturing the diurnal cycle and the duration, frequency, and intermittency of precipitation, and predicting extreme weather from local to global scales and representing orographic precipitation. So these are the goals there, and we're gonna plan. We did some benchmarking. We worked actually quite a while before my time on this, porting MPAS-A, and we did some benchmarking on Summit, the DOE system, with a director's discretionary allocation, and it showed some decent results in weak scaling and also in the strong scaling. So we were pretty happy. I think one of the challenges for us is really, I mean, I think most of the code is ported, but sometimes specific physics packages are not fully ported yet. And this is something we are working very hard on over the summer to really make sure all the physics are ported to the GPU as well. So the full atmosphere code resides on the GPU. So this is one of the still work that is in progress. Our computational plan, and you can see, I mean, we need considerable number of GPU hours, and we plan to start kind of this kind of course resolution to learn, to make sure things work, and then increase the resolution until we go to the 3.75 kilometer runs. And we need about 300, we're going to use 300 GPUs for those runs. And I think the storage is, this is a project where really the post-processing is kind of becoming a bottleneck. We have a project called Region that works on kind of unstructured grids, large-scale post-processing, and so this ties nicely together. But right now, we are definitely seeing the bottleneck is kind of how do we process the unstructured grid data for these large-scale runs. But I think we are pretty confident by the time this project will start, our project Region provides enough tools so that the scientists can process those data efficiently. And again, I think the science need a high resolution really is a good match for the GPU work. Just to summarize, I think we started to refactor some of our community codes to perform on current and future accelerated computing architectures. So far, we've been only focused on a directive-based approach. We've started to explore other approaches. Last summer, we had some students that worked on Cocos, and we are still looking at other approaches there and have more discussion on how do we best refactor our codes to also make them make sure the changes are sustainable. We are working across a lot of the labs to really define science drivers that match well with GPUs, and so that the investments to do refactoring really pays off. So far, we have been doing some good progress for some of our main applications, but there's still a lot of work on the physics modules needs to be done. We have a project Earthworks that really drives some of that. And then I think part of this is also initiating culture change to make our scientists and software engineers aware GPUs are there, and you really need to adopt your models and your code development practice to future-proof your codes. Thank you, and please let me know if you have any questions.
Okay, thank you, Thomas. We have a question here from Kim.
Yeah, thank you, Thomas, for the talk. My question is, how is NCAR seen within the USA HPC community when you announced Derecho that it's an 80 CPU, 20 GPU machine, which is quite different from the other machines that are deployed in the States, mainly full of GPUs?
So you mean more the DOE machines?
That perhaps you are too conservative, or I don't know if you heard something.
Well, that's a good question. I think personally, I think we have been fairly conservative, but I think for me, I think part of it is we have a large community and community code base and user base. So I think for me, I look at this as a stepping stone. Derecho is the GPU participation. It enables porting the codes. I think if you want to really do high resolution runs like what Earthworks is planning to do, you probably need to get allocations on other systems, like getting inside awards on kind of the DOE system. So I think, and we kept some money back. So we have, I think after 2 years, we can actually expand Derecho, and we can add considerable GPU resources if they are used effectively.
You have another question, Sylvie?
Yeah, thank you, Thomas. I was wondering about the plans for this the CESM. Are there clear plans, or is it to move to MPass, or to have the GPU-enabled code, or is it to port or rewrite to have? Are there any plans yet for GPUs?
So MPass. The GPU-enabled MPass will be integrated in CSM. I mean, that's part of Earthworks. But we're going to use the MPAR's ocean model versus CSM uses MOM6. We have another project that we are starting to also port the ocean model to look at the other MOM6 ocean model. And also, I mean, we are working on a proposal to also port the spectral element dynamic equivalent CSM to GPUs. That's still in the works. So we are working on a proposal there to get some funding to do that. So we're still, I think, developing the plans here.
Okay, thank you. I have last question. So my question is, which is the speed up you expect to achieve when running on GPU as minimum threshold to efficiently exploit the GPU partition, considering that your machine is, take this ratio 80/20 CPU GPUs. So, and typically the execution on GPU is not concurrently with the CPU. So if you use a GPU, typically the CPU is not used. So which is the speed up you expect to achieve at minimum threshold in order to efficiently use your machine when running on GPU?
What's the speed up? I think that's a difficult question. I haven't thought about it. I think part of it is we are still exploring. I mean, I think like CM1, I mean, I think we saw a 4 speed up compared to an old CPU, but the porting and optimization is not done. So we hope to get something between 2 and 4. I think this is something that still needs to be seen.
So the very last comment and curiosity from Kim.
Yeah, sorry, I cannot avoid the question because we are in Spain. Where did Derecho names comes from? Because in Spain, Derecho has many meanings, and it would be if you know why you put Derecho to your machine.
So Derecho is the kind of a line of thunderstorms. That's kind of the name. I think I can post the link. It's kind of a line of violent thunderstorms, if I'm not mistaken. I can, if you Google Derecho and thunderstorms, I can post this in the Google Doc, the explanation. I'm not an atmospheric scientist, but I think it comes from an atmospheric phenomenon called Derecho, and I think it's a very violent line of thunderstorms.
Thank you very much.
Okay, thank you again, Thomas, for the presentation.
And we have now Mark Taylor from Sandia National Laboratories to talk to us about E3SM initiative and the C++ based GPU strategy and latest performance. So do we have Mark? We don't see you yet. Yeah, hi.
Oh, can you hear me? And can you see my slides?
We can hear you. The slides are arriving. You can start.
Okay.
And I will tell you 5 minutes before the 20, and then we have 5 minutes questions. Okay?
Okay, great. Thanks. So let me thank the organizers for a very well-run hybrid conference. Hybrid conferences are challenging, but it's worked quite well. So I'm glad I've been able to attend here from New Mexico. Let me just acknowledge some of my collaborators, Andrew Bradley, Oksana Guba, Walter Hanna, Matt Norman, and Shinshu Wan in particular, but also many members of our non-hydrostatic atmospheric group led by Peter Caldwell, and many members of our performance group led by Phil Jones and Sarat Sripathi. So I'm going to talk about work done in the E3SM model, that's Energy Exascale Earth System Model. This is a relatively new, relatively large project funded by the U.S. Department of Energy, started about in 2015 as a fork of the CESM. It's basically a virtual modeling center, about 70 FTEs spread over 8 Department of Energy laboratories. We have a science mission focused on energy and water issues looking out 40 years, so definitely in the climate regime. And a key part of our project is our computational mission, which is to ensure a Earth system model running well on DOE's upcoming exascale computers. All our work is completely open source and on GitHub under this link here, E3SM-project. I also show some results from a companion project that's developing a super parameterized version of the E3SM model. It has some nice features for GPU systems. So we started when we started, our mission was DOE exascale machines, which is in the last couple of years crystallized into basically GPU machines. So not all exascale machines necessarily will be GPU based, but the ones our funding agency is building will be all GPUs now. And so that's our main target. The system we have right now, Perlmutter, that's about 8 megawatts of NVIDIA GPUs, and the 2 exascale machines coming online hopefully later this year or next year. Frontier, that's 30 megawatts of AMD GPUs, and Aurora, which is 40 megawatts of Intel GPU nodes. I'm going to show results from two configurations of cloud resolving or some aspects of cloud resolving atmospheric models running on GPUs. The first one is SCREAM. That stands for Simple Cloud Resolving E3SM Atmosphere Model. That's a traditional global cloud resolving or storm resolving model. One thing somewhat unique about it is that we've rewritten the entire model in C++ using the COCOS performance portability layer to support GPUs. In the second configuration, E3SM-MMF, that's a super parameterized version of E3SM. We started with this using Fortran and directive-based approach, but actually also transitioned to C++, although this project is using a simpler version of COCOS called YACL, which I'll talk about. Starting with SCREAM, we first, in parallel, basically put together the Fortran implementation out of a bunch of components that we were happy with, and then at the same time started rewriting them in C++. So the Fortran implementation and the C++ is based on this non-hydrostatic spectral element dynamical core. For physics, it's the shock, turbulence, parameterization, P3 microphysics, and the radiations RRTMGP. And right now it's only prescribed aerosols. The Fortran code is up and running, and our Diamond results is the contribution to the Diamond cloud resolving model intercomparison project were published last year. The progress of the C++ code, the dynamical core was completed, the port in 2020. We have a supercomputing paper on that. The physics was completed last year, all these physics packages here. The radiation is done by the other project I'm going to talk about, the super parameterization project, and that's actually using YACL, but they work seamlessly together. So they're both C++ based. The driver, I was really hoping to have the full model running to show results at this meeting, but the driver that hooks all these pieces together is not quite done. We just started running that at low resolution recently. So for the remaining slides on the SCREAM performance, I'm going to show benchmarks of just the dynamical core. A little bit about COCOS. So it's this approach, C++ and COCOS, I guess somewhere in between a Fortran and directives approach or a complete DSL approach. We still have to write, most of our code in C++, but we rely on this COCOS library that abstracts the data, the arrays, the multidimensional arrays and their layout, as well as the on-node parallelism. So COCOS does the allocation, keeps the arrays on the GPU. It supports some features which we don't use to let how the data is laid out inside the array to make that a runtime parameter. We haven't found that useful, but we rely heavily on the execution model, the parallel for, and also hierarchical parallelism, where you can launch parallel regions and then within those have parallel for loops. COCOS is very much a C++ approach. It's well integrated into the language, and the COCOS team is actually working with the C++ standards committee to try and get some aspects of this into the C++ language itself. So when we first started, we wanted to make sure we didn't degrade our CPU performance. And here's a plot comparing the C++ code and the Fortran code on a couple CPU architectures and also this since abandoned KNL architecture. The one thing we learned is that the key to good CPU performance is vectorization, and Fortran does an excellent job at auto-vectorizing, and C++, at least in our experience, does not. And we basically had to explicitly vectorize all the loops ourselves. And to do this, we use this concept called PACS, described in this 2019 GMD paper. But once we introduced PACS, we did get the vectorized C++ code to match the Fortran code on traditional CPUs. That's shown in this plot here. This is a normalized strong scaling, so flat is perfect strong scaling. The green is two different, it's comparing the Fortran code and the C++ code on this machine Edison as an Intel Ivy Bridge. The blue is Haswell CPU architecture. So in both cases, the C++ code and Fortran code nearly identical performance. And on KNL, because of this attention to vectorization, our C++ code actually outperforms the Fortran code except when you strong scale out to very thin workloads. But in the high workload, a lot of grid points per node. Fortran could certainly be competitive here if we put the attention to vectorization, started doing a little explicit vectorization in the Fortran code as well. So once we were happy with the C++ code on CPUs, we did a lot of work comparing different CPUs and GPUs. This is a plot that we like to maintain showing single node comparison. So we have a variety of CPUs, usually single node dual socket, but in some cases like the Fugaku, it's a single CPU, single node, and just because of how that chip is produced. And it's from this GMD paper, but we've updated it with additional CPUs and GPUs. This is our die core, so it's a single node benchmark, but the die cores configures as it would in a climate configuration, time steps and such like that, 40 tracers. And then it's kind of a performance metric per watt. So it's grid points per second per watt. Higher is better. It's basically a flop rate. You can think of it that way. And then it's plotted as a function of workload. So on the left, those are very small number of spectral elements or grid points on the node, and on the right, high number of grid points per node. The left is where climate codes are typically run if you're running at the limit of strong scaling, and the right side of the graph is where cloud resolving models are typically run, where you've basically filled up the entire memory of the node with grid points. GPUs are the fastest. The three red curves at the top are all GPU systems, V100s and A100s. They have this characteristic, well known now, that their best performance is in the high workload regime. And with very thin workloads, of course, they actually sometimes are not even competitive with modern CPUs, but they provide real benefit in the high workload regime. A comment on CPUs, they're basically flat in this metric, meaning they get the same performance independent of workload, same flop rate. The curve on the bottom, the dark blue here, is the Intel Ivy Bridge. It dates all the way back to 2012, and our best CPU performance is this pink curve. That's the A64FX. So that's basically 10 years of CPU development. And we're going from 1 to about 3, so a factor of 3 when normalized per watt over the last 10 years in CPUs. And then GPUs, again, for this application, on a per watt basis, we get maybe a factor of 2, 2.5 over the Fugaku chip. The watt numbers there's a little uncertainty in those and the power consumption of these chips. So we put the numbers we use in the legend, and you can change those might change a little, which would change the results slightly. Okay, now then the Scream, again, the dynamical core, this is strong, so that was all single node. This is strong scaling across up to 27,000 GPUs on Summit. This is the the U.S. National Weather Service cloud resolving benchmark. That's a 3 kilometer, run the dynamical core at 3 kilometers, 128 levels, 10 tracers, non-hydrostatic configuration, and everything set to how you would run in production. And this plot, I think there's no CPU results. These are all GPU results comparing different tracer numbers and different tracer algorithms. But our fastest result is a red curve with the semi-Lagrangian transport. And if we can use the whole machine, 27,000 GPUs, the dynamical core runs at 1.38 simulated years per day. So quite expensive, 27,000 GPUs, but obtaining the kind of rates, that will be cut maybe in half in a full climate code, but obtaining the kind of simulation rates that would allow for some climate length simulations. The downside of C++, the C++ code is definitely more complex than the Fortran code. I put one example here. The complexity we don't think this is the case, but some people are worried that we'll end up in a model where only computer scientists can change the code. So we'll have a staff of climate scientists and staff of computer scientists working together. But one advantage of rewriting the entire model in C++ is it does provide a great opportunity to remove decades of very old code that we've accumulated in our Fortran code base over many years. And much of the added complexity in the C++ code shown here is due to the packs needed for vectorization. If you were only targeting GPUs, this wouldn't be would be a little bit more Fortran-like. Okay, so the second application I want to mention, or configuration, I guess, same model, is the MMF, multi-scale modeling framework. That's E3SM atmosphere running with a superparameterization. I don't want to talk too much about the superparameterization concept, but from a performance point of view, let me just mention that it's attractive because there's two components when you run the model this way: the superparameterization itself, which is in our case, is a model called SAM, a 2D cloud resolving model, and the radiation. And these two components in this configuration represent more than 90% of the cost of the full atmosphere. So you can port just those to GPUs and then make efficient use of GPU hardware running superparameterization and keep the entire rest of the model on the CPU. This project started out with OpenACC and OpenMP and had a lot of trouble, just basically got tired of working with compiler bugs and lack of support for modern Fortran features, and switched to C++, maybe a year or two into the project, but not using Cocos, using something called YACL. This is a much smaller, maybe simpler version of Cocos, basically developed internally for the project by Matt Norman and a couple collaborators. It's very Fortran-like, and its specialty is to make it easy to port Fortran codes to C++. In particular, it has Fortran-like multidimensional arrays with Fortran column major ordering, so you don't have to switch that while you're porting, and arbitrary lower bounds that default to 1. And it's on GitHub. Matt has a nice application called Mini Weather I just want to mention because it's a 2D XZ code that he's written in Fortran with OpenACC, OpenMP offload, C++, YACL, and C++ Cocos, so that lets you compare the many different approaches.
Mark, 4 minutes about.
Thank you. Just a couple more slides, I think. So here's a YACL example comparing the original Fortran with OpenACC directives and the C++ YACL version. So this C++ arrays in YACL look very much like Fortran arrays, and the loops are collapsed and replaced by a parallel 4 in this case. So some strong scaling results for the superparameterized model that's shown here in red on Summit. This is the global model running at 0.75 degree, or about 75 kilometers. coupled with a running inside each column a 1 kilometer superparameterization. This shows not the previous speedups. I always tried to normalize by power, but this is node to node. So this is comparing, very far from a power comparison. This is comparing 2 IBM P9s, 1 node of CPUs versus using 6 V100 GPUs. And we like to see at least a factor of 10 in this metric, which we get close to obtaining, at least at the lower node counts in this project, or in this, with this model. The one thing nice about GPU acceleration of the superparameterization, or MMF model, is that this configuration with this 1 kilometer superparameterization can actually achieve 10 simulated years per day on this GPU system. So that really makes it possible to run long, IPCC style climate simulation campaigns where you have to run, 500-year control simulations and things like that. Now, it's not truly cloud resolving superparameterization, but we like to say gets you climate efficiencies and integration rates with some aspects of a cloud resolving model, and does and really benefits from GPU acceleration. Okay, so just to summarize, 2 approaches for C++ performance portability, COCOS and YACL. COCOS is very much a C++-like construct. Our C++ programmers prefer COCOS. It supports many advanced features like hierarchical parallelism. YACL is a much simpler approach, and I'd say our Fortran programmers like the YACL approach. It's currently only supports loop-level parallelism, not hierarchical parallelism, but has nice Fortran-like array syntax. Both of these provide very good GPU performance. And our experience with C++ has been far better than the Fortran plus directive approach. The vendor support on the C++ side is much more mature, especially on AMD and Intel GPUs. I didn't show those results because we are working on those systems, but it's still early access and I don't have permission yet to publicize those results, but soon. The one caveat to the whole C++ approach, the one hesitation I'd say is CPU performance. To get CPU performance, these approaches, COCOS and YACL, really don't address this vectorization issue. And you need to address it by hand, and it, in our experience, requires even more detailed programming than the GPU parallelization. I'll stop here. Thank you.
So thank you, Mark. Actually, we have one question from the Google Doc from Sam. The question is, did you explore the power-saving modes on the A64FX? For example, because on Fogaku, the clock speed can be manually reduced. So have you also explored these power-saving modes?
We did run in both modes. The plot I'm showing is our best performance. And the number I use here is estimated because it's hard to get this number for A64FX. So the 140 watts is probably the high power mode, and the results are from the high power mode, and they would change in the lower powered, some of the lower powered modes. Yeah, but I don't have that data plotted, and we don't know the power accurately enough probably to put both curves on this plot.
Thank you. We have one question from Erwan. Erwan?
Yeah, thank you very much for the talk. I have a question. I'm not an expert in COCOS, just curious about, you say that the CPU vectorization is not so easy, and I heard about like COCOS SIMD backend. Are you aware about that, and can you maybe comment on this?
Yeah, so we do run a Cocos backend on CPUs. I don't remember which one it is, probably the OpenMP threads, and it might have you're saying they have a SIMD backend that might do a better job at vectorization? And sorry, I'm not familiar with that. Our experience was, though, that Cocos did not have a vectorization approach, and we work with a couple other applications that are also, doing developing their own vectorization strategy on top of Cocos. And it may eventually, or may even have started to be something that goes into Cocos at some point.
And the last question from Sylvie.
Yes, thanks very much, Mark. I'm wondering, so you have done an important effort to rewrite the codes in C++ and adapted them to use Cocos. Would you have an amount of FTE years, so just to have an estimate of the effort for the dynamical core and the physics for the atmosphere?
So I really like the comment made earlier that the second time you do it, it would go a lot faster and require a lot fewer FTEs. The first time it takes a long time. So I hesitate to, let me see, here's a little timeline. I would say the dynamical core took us 2 years, maybe 2 years, maybe 4 or 5 people, probably not working full time. And the physics was done in about a year by 3 people, working probably close to full time. So crudely speaking, those are ballpark numbers.
Yeah, it's good. I mean, it gives an order of magnitude. I agree that it's not necessarily very difficult to estimate. What about the sustainability of Cocos? So you're going to be very dependent on Cocos. Are there any issues about the long-term maintenance of Cocos, or what is it?
So yeah, Cocos is within our laboratory system, these Department of Energy laboratories. Cocos is very well funded and supported across a wide variety of applications, not just climate. So I'm not worried about Cocos at all. And YACL is much smaller and basically in-house. We basically support that ourselves in-house. So as long as we're using it, we'll have to support that directly.
Yes, we have a last question from Gijs.
Yes, so can you comment on the level of support from the Cocos development team? I mean, the vectorization issue must have been addressed with them, I guess. So, do you?
So our Cocos, I probably shouldn't comment because I'm not the Cocos developers. I don't work with Cocos code myself. Our Cocos developers do work closely with the Cocos. So our E3SM developers work a lot with the Cocos developers. We're fortunate because a lot of this work is done at Sandia, which is also the laboratory that develops much of Cocos, although it's expanding to the other labs now. But yeah, I don't know how to directly characterize that collaboration.
Okay, so thank you again, Mark.
So we have now a little bit of time for discussion. Before that, we would like, Italo e Picoco within the HPC task force has launched a survey with European models. So we think it is interesting to have this short summary of the survey, and then we will have a little bit of time for further discussion.
Yes, I have just a really quick presentation, 5-minute presentation. I ask the guys over there to share is number 8. Okay, so thank you. The survey we launched and we built a survey in March within the ENES HPC task force. The objective of the survey is just to depict the status of the exploitation of the GPU-based architecture for climate and weather modeling. And so the survey is still open, so I encourage all of the other institutions all to fill in and to provide the information. Up to now, only 7 institutions from a European for Europe have been filled in the survey, and we is not working. Okay, so we asked which models are ready or are going to be under investigation to be ported towards the GPU. We got this answer, so the Icon and Cosmo, as we heard this afternoon, are already available to be run and are executed on GPU. Some other development and investigation are ongoing. As we heard, the model are listed here: ELFRIC, ELMZ, Orchidea, Scheifem, and the others listed in the slide. So we also asked what kind of GPU technology are used to move towards the GPU. We got this answer. The domain-specific language are used for ELFRIC, Cosmo, and Icon. The OpenSCC is the approach most used, but also it appears to be used in the OpenMP in version 5, even if this is not fully supported for all of the compilers and architecture. And we have also asked to estimate the efforts in terms of manpower needed to this kind of activities for the GPU porting. We got as an average overall the answer 2.5 FTE in order to make this investigation. And regarding Cosmo and Icon, a rough estimate is that 10 person years needed for development of the Cosmo on GPUs. And what kind of investigation and what is the status with every models are listed here, but the details we heard during the presentation about the ELFRIC, the primary work has been developed using the PSyclone to refactor some schemes for trial on GPU. About the Namico, they got some preliminary results with some evaluation on Tesla, just measuring a speed up to a factor of 5, and other experience with RPG. Again, some preliminary result running on GPU with a factor of 5 on speed up. And also with the Scheifem model, which is one finite element models based with OpenMP, only the kernel for the application kernel has been ported on GPU with a factor of 3x. And we also asked what kind of strategies for development for the migration is used for porting the model towards the GPU. We got this answer. So 4 institutions prefer and follow an evolutionary approach, so starting from the current legacy code, evolve towards the GPU. 1 institution answered that they prefer to revolutionize, to rewrite and rethink the code, and 2 other institutions is just in the middle with the mixed approaches. And regarding, yes, I will skip this because we heard the presentation. We asked what kind of configuration are actually used for the, let's say, mature GPU-enabled models. So the global configuration at 5 kilometers and at 2.5 kilometers are currently exploiting the GPUs. And another question is about the future plan and investment on GPU-based architecture. Here we have 4 institutions that are planning to invest and to acquire a new architecture based on GPU. and only one is not planned to go toward this architecture. Then we have also asked, but your group is ready to maintain a GPU-based climate model. So here we have a different distribution of the answer. So even if 4 institutions are planning to invest on the architecture, only 2 are actually ready to maintain, and the group and the expert and skill are ready to maintain, such as the GPU-based climate models. And so one of the last questions is, in your opinion, what would be the threshold regarding a part of application using GPUs in order to efficiently exploit the GPU partition? So here we got a heterogeneous answer. For example, the icon group just answered the icon is running entirely on GPU, so is 100% running on GPUs. Then we have also, we got some answer that prefer, and they think that in order to efficiently exploit the CPU, the model must be offloaded on the GPU more than 95% of the model itself. And the last two answers just refer on the speed up. So they think that the efficient exploitation of GPU can be reached if the speed up is a factor of 10, or at most must be compared with the must be greater than the performance obtained by using the same node with the CPU on the same node. And yes, that was the last question, the last slide. So we can open the discussion. We had a lot of topics and a lot of themes can be discussed. For example, one of the first themes we would like to discuss is about the approaches, the revolutionary approaches versus evolutionary approaches. If here in the audience there is any further experience to mention, and what is the best envisioned way to move towards the GPU and rewrite the code, or just evolve the current code.
Or even use a compiler type approach, in fact, like if we can say Loki is a kind of compiler type approach.
Or yes, DSL is another example.
So the question is, any other further experience or other comments people would like to add to the elements we have had at the talks? Some further experience you may have, or?
And
okay. So
Can I make a comment?
If the people from remote could, of course, open the microphone and just intervene directly. So, Mark, do you have a comment? Yeah.
Yeah, I was just going to make a comment. I think the various approaches will all eventually work well. My comment was, if you need to run today, I think you have to do a lot of work by hand. I don't have any. We're not going down the Fortran directive approach, but I think that will eventually work well.
Okay.
Yeah, I mean,
yes.
If I may quickly, so I'd second that in a sense, in that if you talk to recent vendors, especially NVIDIA and others, there's a continued push towards bringing these concepts that we usually express with directives and these sort of high-level things into the actual standard libraries, be that for C or for Fortran. There's some stuff on concurrent do that could sort of allows the compiler to match these things. There is inherent parallelism in C libraries. So we're getting closer and closer to actually the compiler again picking some of these concepts up. We're not there yet, but we're moving much faster towards that sort of ideal, and it's gonna get easier. Is at least the sort of impression that one gets by surveying this.
Jean-Christophe, yes.
Yeah, so I mean, for the Met-Office choice, I don't think we did frame that in a kind of evolution versus revolution.
saying it depends where you are in your scientific process too. So we needed a new model at that point in time. So because we need a new model and we need a new dynamical core, we need to rewrite anyway our model. So we can afford to do a lot of different things. If you are somewhere else in your scientific development, your choices may be different. Yeah.
But in the case, for example, of Icon, where you already have a code that works on GPU, you still have this need of rewriting. So even if, I mean, it seems to be really motivated by the fact that you need a code that goes faster and you need rewriting. Luis, you want to comment?
I think it's more that these are two independent things. The reason for refactoring is, as one of the speakers pointed out, is that you get rid of a lot of old stuff. And typically science codes are not only written by engineers, but by scientists. And scientists have the tendency to introduce a lot of, specific boilerplate code, which is not necessarily required. They never delete anything. They're in that sense more like museums. And so after some time, you need to refactor. And another thing is that, especially in the infrastructure of the models, a lot of nuisances are collected because people tend to hack and not plan to write. And because everything is always very urgent, there is quite some management who says, who cares about quality of the code? We need to have the result yesterday, so go for the crazy stuff. And after maybe 15 years or so, you need to make a cleanup. And that's the refactoring. And it doesn't matter in which language or whatever you do. The problem is it will not really change because in 15 years it looks the same again. But it's like painting your living room.
Yeah, but at the same time, we hear that it might be, to get this separation of concern, there is a need of rewriting. So if indeed we think we need the way of to really be more flexible with the different architectures, it's we have a plus, an added value of having a separation of concern using DSL, using COCOS or whatever approach. There is a need of rewriting. So what about this need? What about having a more just a ported way, just you port? Or do we really need to have this full flexibility for the future? That's a question which is not that easy.
Luis?
Maybe in addition to that, there is another question. Cleaning up the code and rewriting it is something like COCOS means that you have to write a lot of things. And all the examples we listened to today, and that includes Icon, is the dynamical core and the core physical parameterizations. Nobody is really talking about aerosol microphysics, about atmospheric chemistry, about land surface schemes, about paleo stuff, about biogeochemistry in the ocean, about the full carbon cycle. There's nobody talking about. And if you would like to get that properly done, including all the mechanisms you need for reading boundary condition data, blah, 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 then you run into trouble because the speed you gained is immediately endangered because all this external file handling does cost you so much that it's getting hard to maintain. And that's scientific profound questions, and they're have the same living argument as everything else, but you have to redo the world always again and again and again. And I can understand that there are certain scientists who really oppose this, because it's annoying for them that, again, you have to drive into a new hardware or whatever. Your code was getting kicked out, you have to renovate it and get it in again. And you don't get the FTEs. You get the FTEs for the basic work, for the shining, political, nice marketing things.
Okay, we have, please also use, look at the document, so we can use also the Google Doc. Jacob says that if we want today to have portability across different GPU right now, the only the C++ layer is the only option, because OpenSCC will not work on Intel or things like that. So just a comment by Rob. So there might be some other comment. Please do not hesitate to continue the discussion on this.
Milan probably has a comment.
I have a comment and probably an attached question, which is that, well, in the risk of repeating myself, but like yesterday we've already heard a little bit about reduced precision, and I really appreciate all these efforts to port a lot of models. We've seen that in the survey to GPUs, but actually, like, the ball starts really rolling on GPUs once you go to lower precision, right? So we like these typical benchmarks for, I think, the NVIDIA A100 is that if you use 16-bit in their Tensor Core formulation, you actually get it 32 times faster than if you use double precision. And so I was wondering whether any of your strategies going forward into, let's say, the next 5 years or so, let's say the speakers online, but also obviously other people here in the room, whether they include any target towards like really going down in terms of the precision, trying to explore as much as possible, because I'm pretty sure that if we were managed to, like, let's say, run most of the code in half precision, let's say the precision critical parts in single precision, then we're actually really having a big game change, because then we can really exploit what these GPUs are made for, right? So like all these neural network operations which are supposedly run in low precision.
Our colleagues on the web, on the internet, do you have any comment on that, on their precision? Are you exploring that? I heard that NCAR have done some tests and it was not as good as what was obtained with ECMWF when we look in the climate mode, but I'm not fully sure. That's what I heard, but I'm not sure about the source.
Luis? Yeah.
I'll just say we're not, I think it's a good idea, but we're not investigating it right now. Just a quick comment.
So very, very short, 2 comments on this. Why the whole community is running today in double precision has a very simple reasoning. When Cray offered their first vector machine, they had, for the DOE labs, implemented a rather special arithmetic, which unfortunately defined Fortran real as double precision, what we know today. Well, slightly larger exponent and smaller mantissa, but that's the reason, because then people started porting this old stuff, which automatically got double precision, and Cray had a monopole in the situation, and since that people use double precision just because they think it's normal. It hasn't been normal before, and now they are slightly switching back. To be a little bit provocative, we have parts in the code which needs to run in quadruple precision, because if you don't do it, the mathematical methods will fail. So talking about 16-bit floating points, you might be able to do it in certain parts, but there is mathematics behind, and if you're lucky, you can work with FP16. If you're less lucky, it works with FP32, and if you are unlucky, you need FP128. Such is life.
Can I comment on that directly?
Yeah.
I think, I mean, don't get me wrong, I think the invention of double precision is amazing, because that basically meant for the last decades, no one here really had to worry about it, and we were basically able to write down our mathematical models, directly translate them into code. But what I'm basically saying here, that there's an enormous opportunity if we actually, and it's a big challenge, I'm not saying it's easy, right? It's a big challenge to think about how can we write down our algorithms so that they work in double, in single, as well as in half precision. But what I'm basically claiming is that if we actually invested the effort, especially when people already start rewriting models because they're rewriting them for GPUs, that there is an opportunity to kind of think about, oh, actually, if we were to execute this in half precision, maybe we should write in a slightly different way. And I think there's just this opportunity is there, and so we should probably try to pick some of these fruits.
And it's not a new invention. In the late 60s, the Swedish weather service has been reprogramming their CPU to be able to use fixed point arithmetic to save memory, to get more numbers into the machine. Just as an example.
Since I think some of the discussion for the people that are in the room, we can still discuss with the coffee, the dinner this evening. But I would like to give the possibility to our participants from abroad, from online, to say a last word if you want to add something. Since unfortunately you are not there with us to discuss at coffee and dinner on the beach. So
I'll make a comment about GPUs. I think the big win for GPU systems is not going to be IPCC class climate models. It will be cloud resolving, atmosphere only simulations, the kind of simulations that run well on those machines. And the IPCC stuff is going to be on CPUs for a long time to come. The prediction.
Interesting. I think this is, it's clear that at each time we see with GPU the high resolution, very high resolution, and yeah, we have all the needs, and yeah, that's a good point. Whether indeed that will be the case, at least for the next IPCC. I don't know if it will be longer than that. We don't know. Are there any reactions, Michael or Thomas?
I second Mark's comment. I mean, I think this is one of the reasons why we have these science engagement and really try to identify the science cases that work well on GPUs and leave the others alone, basically. And these are, I mean, we have engaged with each of the labs in NCAR and saying, okay, what are the science you want to do that requires GPU or that would map nicely to GPUs versus like typical other simulations that will probably stay on CPUs. So I definitely second Mark's comment here.
Yeah, I mean, I can only add to that and effectively the same thing. There's probably something to it. I think we'll still see quite a significant change in the style that GPUs will be used as the next generations come along. What we nowadays call the GPU is not necessarily going to be the same thing in a few iterations' time. But alongside that, I think the programming models will evolve as well. So it'll be very much a case for specialization, figuring out which type of model actually benefits from this and which type of model does not. And that's still active research, like anything is really. So yeah, thanks.
So, thanks very much to all the speakers in here and virtual. And we close the session. Thanks very much.
Thank you. Thank you.
Bye. And
yeah, but we close this.